Hello there, and welcome to the Cosmographer. Everything humanity knows about planets was learned from 8 worlds, and the universe has spent 30 years quietly taking that education apart. On this list is a planet that orbits its star backward, beneath clouds made of quartz. There is a planet darker than coal that glows like a pulled ember, and a blue world where the rain is molten glass, flying sideways on winds of 8,700 kilometers per hour. There is a world whose entire year lasts 17 hours and 40 minutes, circling a star you can find tonight with your naked eye. And there is a planet astronomers have watched beginning to die, a world whose ending has a measured date. Tonight, across 3 unhurried hours, we count down the 10 strangest planets in the known universe, everyone real, everyone verified, and every open question honestly labeled. And the planet at number 1 was seen exactly once, for 56 days, through its shadow alone, and has never been found again. Get comfortable and settle in. If falling asleep to worlds stranger than fiction sounds like your kind of night, a quick like and subscribe helps this channel reach more curious minds like you. Because by the end of this countdown, you will know why the strangest planet we know of is one that nobody can find. Now, let's begin at number 10. Number 10. The first second Earth. Everything humanity believed about planets was learned from 8 examples. For most of recorded history, the word planet meant one of a small family of lights that wandered against the fixed stars, and once telescopes sorted them out, that family settled at 8 worlds circling one ordinary yellow star. Every rule we wrote came from them. Planets orbit in the same direction their star spins, because they condensed from the same spinning cloud. Rocky worlds keep close to the star, and giants keep their distance. Water is ice when it is cold, and steam when it is hot. Rings are a modest decoration, worn most famously by Saturn, whose bands of drifting ice remain the most beautiful structure the solar system ever built. 8 examples, 1 set of rules, and no reason to doubt any of it. Then, beginning in the middle of the 1990s, astronomers started finding planets around other stars, and the rulebook began to come apart almost immediately. As of tonight, the count of confirmed worlds beyond our solar system stands near 6,000, with thousands more candidates waiting in the queue. Spread across that catalogue are planets that orbit backward, planets darker than coal, planets made largely of water that cannot boil, planets with no star at all, and at least one object whose rings would swallow half the distance from the Sun to Venus. Every one of them was impossible by the old rules. Every one of them is real. Over the next 3 hours, we will make our way down a list of the 10 strangest planets in the known universe, counting from number 10 to number 1. The ranking is not about size, and it is not about distance. It is about how completely each world defeats explanation. The list begins with planets that merely disappointed us, moves through worlds whose physics are extreme but understood, and descends into worlds whose existence itself has no agreed answer. And at number 1 sits a planet that astronomers observed for 56 days, through its shadow alone, and have never been able to find again. We begin 20 light-years from Earth, with the first planet humanity ever mistook for a second home. The star is called Gliese 581, and it sits in the constellation Libra, close enough that its light reaches us in about 20 years. It is a red dwarf, the most common kind of star in the galaxy, and also one of the dimmest. Gliese 581 shines with barely more than 1% of the Sun's light. If you swapped it into the center of our solar system, noon on Earth would look like a fading dusk, and the oceans would freeze from pole to pole within a matter of years. Red dwarfs are small, cool, and extraordinarily patient. They burn their fuel so slowly that they will outlive the Sun by hundreds of billions of years. Whatever happens in the universe's long future, stars like this one will be there to watch it. In April of 2007, a team of astronomers led by Stefan Udry of the Geneva Observatory announced that this dim, patient star had a planet unlike any found before. The team had been using an instrument called HARPS, mounted on a 3.6-meter telescope at the La Silla Observatory, high in the dry mountains of Chile. HARPS does not photograph planets. It watches the star itself, measuring the tiny wobble that an orbiting planet's gravity drags out of it. The wobble that revealed this planet was delicate almost beyond belief. The star swings back and forth at roughly the pace of a person walking briskly, and HARPS detected that walking pace sway from 20 light-years away. The planet was named Gliese 581c, and its numbers made astronomers sit up at their desks. Its minimum mass came out near 5.5 times the mass of the Earth. In 2007, that made it one of the smallest planets ever found around a normal star, at a time when nearly everything in the catalogue was a giant the size of Jupiter or larger. Small for a planet hunter means rocky. Rocky means a surface. And a surface means somewhere to stand. The orbit was the detail that made the front pages. Gliese 581c circles its star at about 7% of the distance from the Earth to the Sun, completing a full year in just under 13 days. Around our Sun, that orbit would be a death sentence, closer in than Mercury by a wide margin. But around a star with 1% of the Sun's output, everything shifts inward. The zone where liquid water can survive, the band astronomers call the habitable zone, wraps tightly around a red dwarf like a family gathered close to a small fire. At first analysis, Gliese 581c appeared to sit inside that band. The average temperature estimates landed between 0 and 40 degrees Celsius, the range of a cool morning and a hot afternoon on Earth. The announcement traveled around the world in a day. Newspapers called it the first habitable planet found beyond our solar system. Headlines called it a second Earth. It was described as a place where water could pool into oceans, where the temperature might suit life, where humanity might one day aim its ships. After a decade of finding nothing but scorched giants, the galaxy had produced something that sounded like home, and it was practically next door. 20 light-years against a galaxy 100,000 light-years across is the house across the street. The excitement produced one of the strangest artifacts of the space age. In October of 2008, a giant radar dish in Yevpatoria, Ukraine, called the RT-70, turned toward Gliese 581 and transmitted a package of messages into the sky. The transmission was called A Message from Earth, and it carried 501 entries selected from a public campaign, written and chosen by ordinary people. There were greetings addressed to whoever might be listening. There were photographs and drawings. There were short letters from children. The messages left the dish at the speed of light, and they do not stop, and they cannot be recalled. Sometime around the year 2029, that signal arrives in the neighborhood of Gliese 581 and washes over whatever is there. Here is the strangeness at the heart of this planet, and the reason it opens our list. By the time those letters were a year into their journey, the second Earth was already dissolving under scrutiny. When atmospheric scientists worked through the details, they found that the first temperature estimates had ignored the one thing a real planet cannot ignore, which is its own air. Any atmosphere thick enough to hold water on Gliese 581c would also trap the star's heat, and the trap runs away. Carbon dioxide builds, the surface warms, the oceans steam into the sky, and the steam traps heat faster still. The models kept arriving at the same destination, which is the planet next door to us in our own solar system. Venus, where the air presses down like a kilometer of ocean, and the ground glows at temperatures that melt lead. The first habitable exoplanet, on closer inspection, was most likely a furnace with good publicity. There is a detail that makes the picture stranger still. Orbiting so close to its star, Gliese 581c is almost certainly tidally locked, the way our moon is locked to the Earth. One hemisphere faces the star forever. The other faces away forever. Astronomers call worlds like this eyeball planets, because in the imagination they resemble an eye, one side bright and fixed, the other dark. On the day side, the red star never rises and never sets. It simply hangs there, nailed to the same place in the sky, 4 times the width of our full moon, for the entire life of the planet. Hold that image of the full moon, by the way. It is a yardstick we will need again at the very end of this list, for a sky far stranger than this one. Between the two hemispheres runs a boundary that planetary scientists find genuinely tantalizing. It is the terminator, the ring of permanent twilight that separates endless day from endless night. If Gliese 581c has any temperate ground at all, any place where the furnace of the day side and the hard freeze of the night side balance into something survivable, it is that ring. A band of forever sunset wrapping an entire world. Picture standing there for a moment. You are on a plain of dark rock, in light the color of embers. To one side, the horizon glows, and the land runs off toward a permanent red daylight you could never survive. To the other side, the sky deepens through purple into a night that has lasted for billions of years. Ahead of you, balanced on the boundary of the two, the star sits swollen and motionless, just at the edge of the world, dim enough to look at directly, wide enough to blot out 4 full moons. Nothing about the scene changes. There is no morning coming. The wind, if there is wind, is the only clock. You are standing in the one place on this planet where the temperature might allow you to stand at all, a strip of borrowed comfort between 2 eternities, and the star watches you like a shut eye that never opens and never closes. The story of this planet's star system has one more turn, and it taught astronomy a lesson it still repeats to students. The excitement around Gliese 581 kept the world's spectrographs pointed at it for years, and the star seemed to keep giving. In 2010, a team announced a 4th and 5th planet, and one of them, called Gliese 581g, appeared to sit dead center in the habitable zone. It was nicknamed Zarmina's world, and for a while it was the most famous planet in the galaxy, hailed as the most Earth-like world known. But other teams could not find it in their own data. The signal flickered depending on who was looking and how. The consensus today is that Gliese 581g was very likely never a planet at all, but an illusion assembled from the star's own magnetic weather, star spots masquerading as a world. A neighboring claimed planet, Gliese 581d, fell to the same doubts a few years later. The system that gave us the first second Earth also gave us the first great lesson in how easily hope can contaminate data. Through all of it, Gliese 581c itself has held. Its signal is solid, confirmed again and again, a genuine super-Earth on a genuine 13-day orbit. What changed is only what we believe it to be. It entered the catalogue as a garden and remains there as an oven. And the letters are still on their way. 501 messages from the people of Earth, written to a world that was already turning out to be uninhabitable while the ink was still fresh, arriving around 2029 regardless. Whether anything ever reads them, the universe now permanently contains a bundle of human hope, moving at the speed of light, addressed to the wrong house. It is worth understanding just how new this kind of discovery was, because the method itself is a small miracle of patience. Until 1995, the count of known planets around sun-like stars beyond our own system stood at 0. Then Michel Mayor and Didier Queloz, working from an observatory in the south of France, detected the wobble of a star called 51 Pegasi, tugged by an unseen giant circling it every 4 days. That single measurement opened the era this entire list lives in, and it eventually earned the two of them the Nobel Prize in Physics. The instrument that found Gliese 581c, HARPS, was the direct descendant of that work, built by the same tradition of Swiss precision, and it pushed the technique to the edge of what physics allows. To catch a 5-Earth mass planet around a red dwarf, HARPS had to hold its calibration steady enough to notice a star's velocity changing by about the speed of a jog, sustained across months of separate nights, through the shimmer of Earth's own atmosphere. It is one of the quietest forms of exploration our species has ever practiced. No engines, no landings. Just a spectrograph in the Chilean mountains, listening to starlight closely enough to feel a small world leaning on its sun. There is also an honest gap in the file on Gliese 581c, and it should be named plainly. Because the planet does not transit its star, astronomers have never measured its size, only the minimum version of its mass. That means no density, and no density means no certainty about what the world actually is. It is usually described as rocky, and at 5.5 Earth masses it may well be, a true super-Earth, with a surface and geology and weather. But it could also carry a thick envelope of gas, a miniature Neptune with no surface at all, and the letters aimed at it would then be addressed not to a scorched landscape, but to an endless fall through hot cloud. 2 decades of progress in this field have taught a consistent lesson, that worlds in this mass range come in both varieties, and telling them apart from 20 light-years away is genuinely hard. The first planet humanity ever called habitable is still, in the most basic material sense, a stranger. And red dwarf planets carry one more layer of difficulty, one that has only grown sharper since 2007. Small stars are not gentle. Red dwarfs, especially young ones, are prone to violent magnetic flares, outbursts that can briefly double their brightness and lash their close-in planets with radiation. A planet 14 times closer to its star than Earth stands in the front row for every one of those events. Some models hold that flares like that, repeated over billions of years, can strip a close planet's atmosphere entirely, leaving bare rock facing an unquiet star. Others suggest a thick enough atmosphere or a strong magnetic field could ride it out. The question matters far beyond this one system, because red dwarfs make up roughly 3 out of every 4 stars in the galaxy. Whether their tightly held planets can keep air on their faces is one of the standing questions of the field, and the answer will decide whether the galaxy's most common stars are surrounded by living possibilities or by billions of stripped stones. Gliese 581c was simply the first world that forced the question into the open. 20 light-years is a distance worth feeling properly before we move on, because it frames everything the letters mean. The fastest objects humanity has ever launched, the Voyager probes, travel at roughly 17 kilometers per second, and at that pace the crossing to Gliese 581 would take well over 300,000 years, 60 times longer than recorded history. No ship we can currently imagine makes that trip. But the radio message crosses in 20 years flat, because light pays no fare. That asymmetry is the quiet truth of our era. We can speak across distances we cannot travel, and so our first genuine contact with the galaxy has taken the form not of footprints or flags, but of mail. And the mail is durable beyond reckoning. Radio waves do not stop at their address. After brushing past Gliese 581 in 2029, the transmission simply continues outward, thinning but never vanishing, a shell of human voices expanding through the galaxy at the speed of light for as long as the universe cares to carry it. The letters to the wrong house will eventually pass every house there is. That is the gentlest kind of strange this list contains, a planet that broke nothing but our expectations. From here, the rules themselves start to fail. The next planet on this list kept its orbit, but it runs that orbit in the wrong direction entirely. Number 9. The planet that orbits backward. Every planet you have ever stood on, seen, or heard of in our solar system obeys one quiet rule so completely that most people never learn the rule exists. They all orbit the Sun in the same direction that the Sun itself rotates. Mercury, Venus, Earth, Mars, the giants, the dwarf planets, the asteroids, the icy debris beyond Neptune, all of it circulates counterclockwise when viewed from above the Sun's north pole, matching the spin of the star at the center. This is not a coincidence. It is a birthmark. The Sun and its planets condensed together from a single collapsing cloud of gas and dust, and a collapsing cloud spins. Whatever direction that cloud turned, the star inherited it, the disk inherited it, and every planet built inside the disk inherited it too. The direction of a planet's orbit is a memory of the cloud it was born from, preserved for 4.5 billion years. Which is why the 9th planet on our list caused the reaction it did. About 1,000 light-years away, in the constellation Scorpius, there is a hot yellow-white star, catalogued as WASP-17. In 2009, astronomers announced that it has a giant planet, WASP-17b, crossing its face every 3.7 days. And that planet orbits backward. It travels around its star in the direction opposite to the star's own spin, against its birthmark, against the memory of its own cloud, against the one rule every world in our solar system keeps without exception. The discovery itself came from an instrument that sounds almost too modest for the job. The wide-angle search for planets, known as Super-WASP, is not a great observatory with a mirror the size of a swimming pool. It is an array of camera lenses, the kind of telephoto lenses a sports photographer might carry, bolted together on mounts in South Africa and the Canary Islands, photographing huge stretches of the sky over and over through the night. The strategy is patience rather than power. Watch hundreds of thousands of stars and wait for any of them to dim by 1% on a regular schedule, the tiny shadow of a planet crossing its star. It is one of the most productive planet-hunting strategies ever devised, and it will hand us another world before this list is done, including the one waiting at number 1. Measuring the direction of an orbit, though, takes more than a shadow. To catch a planet driving the wrong way, astronomers use a piece of physics called the Rossiter-McLaughlin effect, and it is worth 30 seconds of your night because it is genuinely elegant. A spinning star has one edge rotating toward us and one edge rotating away. The approaching edge has its light compressed slightly toward the blue. The retreating edge is stretched slightly toward the red. When a planet transits, it covers one edge first and the other edge later, and by watching which tint of the starlight vanishes first, astronomers can tell which direction the planet is moving relative to the star's spin. When they ran that measurement on WASP-17b and confirmed it again the following year, the answer refused to cooperate with any comfortable expectation. The planet's path is tilted so far that it is fully retrograde. It meets the rotation of its own star head-on. Something had to have happened to this world. A planet cannot be born orbiting backward, for the same reason a river cannot flow uphill from its source. It formed, like all planets, moving with the disk. Then, something threw it. The leading suspects are gravitational, and both are violent in the patient way that gravity is violent. One possibility is a close encounter with another giant planet in the same system, a slingshot duel that hurled one world inward on a wild, tilted path and may have ejected the other into interstellar space entirely. The other possibility is called the Kozai mechanism, in which a distant, massive companion, another planet or a faint star, slowly tips a planet's orbit over tens of millions of years, wrenching it through steeper and steeper angles until it flips past vertical and comes down on the far side, orbiting in reverse. Either way, the backward orbit is a scar. WASP-17b is a fossil of some ancient catastrophe, and the evidence of that catastrophe is written not on its surface but in its direction of travel. The strangeness of this planet does not end with its path. WASP-17b is also one of the puffiest planets ever found. Its mass is about half the mass of Jupiter. Its radius is nearly twice Jupiter's, which means its volume, the amount of space it fills, is more than 7 times Jupiter's. Half the material, 7 times the room. Work out the density of a world like that, and the number lands at roughly 7% of Jupiter's density. For comparison, Saturn is famously the least dense planet in our solar system, light enough that it would float in a big enough ocean. WASP-17b is several times less dense than that. It is less dense than styrofoam. If you could somehow set it on a cosmic table, it would sit there like a soap bubble wearing the mass of 160 Earths. A planet gets this way by being cooked. WASP-17b orbits its hot star at about 1/7 the distance of Mercury from the Sun, and its day side runs around 1,500 degrees Celsius. That heat pumps energy into the atmosphere faster than the planet can shed it, and the atmosphere answers by swelling. The outer layers inflate like bread in an oven, thinning as they rise, until the planet's grip on its own upper air becomes tenuous. What is left is a world stretched to the edge of what a planet can be, a giant so distended that its outline is more suggestion than boundary. And in that swollen atmosphere, astronomers recently found something no one had ever seen anywhere. In October of 2023, a team using the James Webb Space Telescope's mid-infrared instrument reported the signature of quartz in the clouds of WASP-17b. Quartz, crystalline silica, the mineral of Earth's beach sand and granite countertops, drifting through an alien sky as clouds. The crystals are tiny, roughly 10 nanometers across. 10,000 of them laid side by side would just about span a single human hair. On Earth, quartz is the definition of solid ground. On WASP-17b, the temperature is so high that rock-forming minerals behave the way water behaves here. They evaporate, they rise, they condense into cloud decks, and presumably, somewhere in that atmosphere, they fall. Weather made of gemstone dust. Sand that exists before any beach does, suspended in the sky of a planet moving the wrong way around its star. It is worth pausing on what a sky like that would look like from the inside. Silicate crystals are excellent scatterers of light. An observer drifting in the upper decks of WASP-17b, if any observer could survive there for even a moment, would ride through veils of glittering mineral haze, backlit by a star that fills a fair portion of the sky, in winds hot enough to keep rock in its gaseous form. Above them, that star would cross the sky in a direction no earthly sky has ever shown, because the planet under their feet is running its year in reverse. Astronomers still argue about parts of this world. The exact machinery that keeps it so inflated is not fully settled, since simple starlight heating falls a little short in some models, and tidal flexing may be quietly helping from inside. Which of the two violent histories flipped its orbit remains an open case, and no companion guilty of the crime has been identified. What no one argues about is the measurement itself. The planet is there. It is enormous. It is nearly empty. Its clouds are crystal, and it is moving backward. Here is the thought to carry out of this one. In our sky, every planet, every month, every tide keeps the same ancient direction, a 4.5 billion-year habit inherited from a cloud. It took finding other suns to learn that the habit is optional. Direction itself, the most basic fact of a world's existence, turns out to be negotiable, and the universe was under no obligation to mention that until we looked. The physics trick behind that measurement deserves its footnote in history, because it is older than the field it now serves. The Rossiter-McLaughlin effect is named for two American astronomers who first measured it in 1924, not on planets, which no one could then detect, but on pairs of eclipsing stars, one crossing the face of the other. For 80 years, the effect was a specialist's curiosity, a subtle distortion in the light of double stars. Then the exoplanet era arrived, and the old tool turned out to be exactly the key needed for a question nobody in 1924 could have asked. Which way do other worlds go around their suns? The answer, gathered planet by planet over the past 2 decades, has been genuinely humbling. Among the hot Jupiters, the close-in giants that surveys find most easily, roughly a third ride orbits that are significantly tilted from their star's equator, and a small, remarkable handful, led by WASP-17b, are fully reversed. Our solar system's tidy, flat, one-direction architecture, the layout every classroom model presents as simply how planets are, turns out to describe only part of the galaxy's inventory. A meaningful fraction of planetary systems have been through chaos. That chaos connects to a deeper puzzle that WASP-17b wears openly, the puzzle of how a giant planet ends up this close to its star at all. A world of half a Jupiter mass cannot form on a 3.7-day orbit because the neighborhood so close to a young star is too hot and too small to supply the raw material. Giants must be born far out, in the cold country beyond the frost line where ices survive, and then travel inward. Astronomers have 2 broad theories of that journey, and they leave different fingerprints. A planet that migrates smoothly, surfing inward through the gas of its birth disk, arrives on a calm, flat orbit, aligned with the star's spin. A planet that arrives through violence, flung by a rival, or tipped over eons by a distant companion, arrives on a tilted, eccentric, sometimes backward path. Every misaligned hot Jupiter is therefore a vote for the violent road, a survivor of gravitational war rather than an orderly commuter. WASP-17b, the most decisively backward of them all, is the strongest single vote in the ballot box. When you look at its retrograde year, you are looking at the aftermath of one of the 2 ways solar systems are made, the way that involves worlds throwing each other across the sky. There is one more consequence of the backward orbit worth carrying with us, because it points, quietly, at a planet waiting further down this list. Orbits that oppose their star's spin are not stable in the deepest long term. Tides between the star and a retrograde planet do not push it outward, the way our moon is slowly pushed away from Earth. They drain the orbit instead, patiently, over billions of years, drawing the planet down. A world like WASP-17b is not merely a fossil of past violence. It is also, on the longest timescales, a slow-motion casualty of it, bound eventually to spiral into the star it defies. Astronomers have already caught one hot Jupiter in exactly that act of falling, with its remaining lifetime measured and its ending scheduled, and we will stand at its bedside at number 2 tonight. The backward planet at number 9 is an earlier chapter of the same story, still proud, still enormous, still running the wrong way, with the bill not yet due. The star itself deserves a line in this portrait because it is part of why the planet is so extreme. WASP-17 is a hot star of the class astronomers label F-type, larger, brighter, and younger burning than our Sun, spinning quickly, pouring out a harsher light. Planets of fast-spinning hot stars are disproportionately the misaligned ones, a pattern the field noticed once enough examples accumulated, and theorists suspect such stars either tilt their planets more easily or erase tilts more slowly. Around a star like this, WASP-17b's dayside receives an unrelenting flood of energy that would bleach our own sky white, and it is that flood, working on a half-Jupiter of material, that inflates the planet like held breath. If you wanted to design, from scratch, the conditions for producing a backward, swollen, crystal-clouded giant, you would draw something very close to this system: a hot, bright star, a violent, dynamical history, and a planet caught between them, with nowhere to put the energy but into its own size. Consider also what a calendar would even mean on such a world. Its year, the single backward lap around the star, lasts 3.7 days. Its rotation is almost certainly tidally locked, one face pinned starward, so there is no sunrise anywhere, ever. A year with no days in it, run in reverse, under a sky where the stars themselves parade in the direction no earthly sky has ever shown them. Timekeeping, that first human science, would have to be reinvented from nothing there, and the reinvention would begin from a fact no earthly astronomer before 1924 had tools to even ask about: which way the world is going. The survey that found this world deserves its own line in the ledger, because its fingerprints are all over this list. SuperWasp began as a proposal so cheap it was nearly unfundable, a plan to bolt commercial camera lenses onto a shared mount and let them stare. It grew into the most successful ground-based planet hunt ever conducted, with 2 robotic stations, one on La Palma in the Canary Islands watching the northern sky, one in South Africa watching the south, together monitoring millions of stars and delivering nearly 200 confirmed worlds. Its planets carry its name in order of confirmation: WASP-1b, WASP-2b, and onward, a plain numbering that hides how strange the catalogue became. Number 17 was the backward one. Number 12, still ahead of us tonight, is the dying one. When the history of this field is written, the great space telescopes will take the portraits, but an honest account will note that a remarkable share of the strangest worlds were flushed out of hiding by camera lenses a wedding photographer would recognize, mounted in pairs on a concrete pier, doing the same simple thing every clear night for 20 years. WASP-17b also turned out to be a founding member of a class astronomers now call the puffy planets, and the class has only grown stranger since. Surveys have since turned up worlds with densities lower still, planets compared in the literature with a straight face to cotton candy, giants of near Saturn size carrying barely a Neptune of mass. Each one poses the same standing problem this planet posed first, that our models of how gas holds together under a star's heat struggle to keep anything this diffuse from either collapsing or blowing away. The puffy planets persist anyway, indifferent to the difficulty. It is becoming one of the field's recurring lessons, met over and over down this list. The universe does not check our models before deciding what to keep. But a backward orbit, in the end, is still made of familiar material: hydrogen and helium and mineral cloud. The next world on our list is stranger in its substance itself. It is built around a form of water that should not exist, water that stays solid at temperatures that would melt lead. Number 8. The world of burning ice. Ice is one of the first facts a human being learns about the universe. Water gets cold, and it hardens. Water gets hot, and it steams away. The rule is so reliable that we build our language on it. Ice means cold. Everyone on Earth, in every era, in every climate, has agreed on this without ever needing to say it aloud. The 8th planet on our list exists to demonstrate that even this rule, the one we learn before we can talk, is local custom rather than cosmic law. 32 light-years away, in the constellation Leo, a dim red dwarf called Gliese 436 holds a planet whose interior is very likely dominated by ice that is hotter than a self-cleaning oven. Astronomers, who are ordinarily careful with language, describe it with a phrase that sounds like a contradiction and is not. They call it Burning ice. The planet is Gliese 436b, and its discovery in August of 2004 was itself a landmark. It was found by the radial velocity team of Paul Butler and Jeffrey Marcy, two of the most prolific planet hunters of the first exoplanet era, and it weighed in at about 22 times the mass of the Earth, with a diameter around 4 times Earth's. That makes it a close cousin of Neptune in bulk. In 2004, nothing that small had ever been found orbiting a normal star. The catalogue until then was a parade of giants, because giants are what the early instruments could see. Gliese 436b was the first hint that the galaxy's planet population extended far below Jupiter, down toward worlds of more modest, more familiar scale. 3 years later, in 2007, a team led by Michael Gillen caught the planet crossing the face of its star. That transit changed everything, because a transit gives you a planet's true size, and size plus mass gives you density, and density tells you what a world is made of. Gliese 436b became the first Neptune-sized planet ever observed in transit, and its numbers told a strange story. The planet is too dense to be a ball of hydrogen and helium, and not dense enough to be rock and iron. The bulk of it, the models agree, must be water. An enormous mantle of water wrapped around a rocky core, buried under a modest envelope of hydrogen and helium gas. Here is where the familiar rule fails. Gliese 436b orbits its star at less than 3% of the distance from the Earth to the Sun, 13 times closer than Mercury sits to our own star, completing a full year in about 2.6 days. Even around a dim red dwarf, that proximity keeps the planet's temperature near 440 degrees Celsius, hot enough to melt lead with room to spare. Water at that temperature should be steam, and nothing but steam. And near the surface, it surely is. But descend into the planet, and the pressure begins to climb, and pressure changes what water is allowed to do. The water molecules far inside Gliese 436b are squeezed by the weight of an entire world sitting on top of them. For comparison, the deepest point in Earth's oceans, the Challenger Deep, presses down with about 1,000 times the pressure of the air in your room, and that pressure is already enough to deform steel instruments. The pressures in the interior of Gliese 436b run to millions of atmospheres. Under that kind of compression, water molecules no longer have the freedom to fly apart as vapor, no matter how much heat urges them to. They are packed so tightly that they have nowhere to go but into rigid order. They lock into dense crystal structures, forms of solid water that physicists label with Roman numerals, Ice 7 and Ice 10, phases that do not occur naturally anywhere on the surface of the Earth. This is ice that owes nothing to cold. It is solid because it is trapped, held in crystalline formation by pressure alone, at temperatures that would turn the contents of your freezer into a flash of steam. Sit with that image for a moment, because it rewards patience. The substance filling your glass tonight, the substance falling as snow somewhere on Earth right now, has alternative lives. Squeeze it hard enough and it becomes a mineral, a hot black-red solid far inside an alien world, closer in its behavior to rock than to anything you have ever poured. The universe keeps alternative versions of even our most familiar things, and it stores them in places we can never visit, and we know about them anyway, because a dim star 32 light-years away wobbles by the width of a walking pace. If burning ice were this planet's only strangeness, it would still have earned its place on the list. But Gliese 436b is a world of stacked anomalies, and the second one announced itself in ultraviolet light. In 2015, a team led by David Ehrenreich pointed the Hubble Space Telescope at the system during transit, observing in wavelengths where the star is dim and hydrogen gas glows in absorption. In visible light, the planet's transit dims the star by well under 1%. In ultraviolet, the star dimmed by more than half. Something enormous was crossing the star, something far larger than the planet itself. That something is a cloud of escaping hydrogen, torn from the planet's atmosphere by the star's radiation and streaming behind it in an immense trailing plume. The Discovery team nicknamed it the Behemoth. The cloud is roughly 50 times the size of the star it orbits. A planet the size of Neptune is dragging a veil of gas that would engulf our Sun 50 times over, sweeping around a 2.6-day orbit like the train of a wedding dress, 1,000 times too long for its wearer. Gliese 436b is, in the most literal observational sense, a planet doing an impression of a comet. The numbers behind the plume are stranger than the image. The planet is losing on the order of 1,000 tons of atmosphere every second. That sounds like a death sentence, and for a smaller world it would be, but 1,000 tons a second, sustained for the entire remaining life of the universe's stars, barely dents a planet of 22 Earth masses. The current estimate is that Gliese 436b has lost only around 1 part in 1,000 of its atmosphere over its whole history. Its star is too dim, too cool, too gentle to finish the job. The planet bleeds forever and is never wounded, a leak with no consequence, wearing its own slow escape as a costume. Then there is the matter of how this world travels, which may be the strangest fact of all. In 2017, astronomers finally measured the orientation of the planet's orbit relative to its star's spin, the same kind of measurement that exposed the backward path of WASP 17b 1 item ago. Gliese 436b, it turns out, does not orbit around its star's equator the way planets are supposed to. It travels nearly over the star's poles, circling at close to a right angle to the star's rotation. And its orbit is measurably stretched, noticeably out of round, when every law of tides says a planet this close, on a 2.6-day year, should have been kneaded into a perfect circle billions of years ago. Tides on a close orbit act like a hand smoothing a bedsheet, relentlessly, forever. Something keeps wrinkling this sheet. Both oddities point to the same invisible suspect. A massive unseen companion farther out in the system could have dragged Gliese 436b onto its polar path and could be maintaining its stretched orbit against the smoothing of the tides. The mechanism would be the same slow Kozai tilting that stands accused of flipping WASP 17b. But here the culprit has never been found. Searches have turned up candidates and ruled them out again. The planet's strange path is evidence of a hidden hand, and the hand remains hidden. And still the planet has one more refusal in it. When astronomers used the Spitzer Space Telescope to study the chemistry of its atmosphere, they expected methane. At the temperature of Gliese 436b, basic chemistry says carbon should overwhelmingly take the form of methane, the way it does on Neptune and Uranus and Jupiter. Instead, Spitzer found an atmosphere rich in carbon monoxide and strangely starved of methane, thousands of times less methane than the models demanded. Nearly 2 decades later, that deficit has never been fully explained. Perhaps the atmosphere churns violently enough to dredge up carbon monoxide from hot depths. Perhaps the chemistry is being driven by radiation in ways the models undercount. The honest label, and this list will use honest labels all the way down, is unresolved. So, stand back and look at the whole object. A Neptune-sized world on a 2.6-day year around a quiet red star. A mantle of ice that burns. A comet's tail 50 times wider than its sun. A polar orbit that should not exist, bent out of round by a companion nobody can find. An atmosphere missing the one molecule chemistry insists it should have. Any one of these would make a career for the astronomers who explained it. This one planet carries all 5, 32 light-years from your bedroom. Gliese 436b earns its anchor place on this list because it is the moment the countdown stops being about broken expectations and starts being about broken categories. Ice that is not cold. A comet that is a planet. An orbit with no explanation. The words themselves start to fail here, and we are only at number 8. The science of water's hidden forms is worth a slow minute of its own, because it is one of the most quietly astonishing bodies of knowledge our species owns. Ordinary ice, the ice of ponds and freezers, is called Ice 1, and it is a strange substance in its own right, less dense than the liquid it froze from, which is why it floats, and why lakes freeze from the top down, and why fish survive winter. But Ice 1 is only the first entry in a long ledger. Compress water in the laboratory between the polished faces of 2 diamonds in a device called a diamond anvil cell, and it begins moving through a catalogue of alternative crystal structures, each with its own geometry, each stable in its own territory of pressure and temperature. Physicists have confirmed roughly 20 distinct phases of ice, numbered in order of discovery. Ice 6 forms at pressures around 10,000 atmospheres. Ice 7, the phase expected in bulk, inside Gliese 436b, appears above about 20,000 atmospheres and remains solid across a wide range of heat. Ice 10, deeper still, at pressures approaching 1,000,000 atmospheres, is barely water anymore in the familiar sense, its hydrogen atoms surrendering their identity to a symmetric lattice. Every one of these substances is real, made on Earth, held for moments between diamonds. What Earth cannot do is keep them. Release the pressure, and they relax back into ordinary water, the exotic structure dissolving like a dream on waking. A planet, though, never releases the pressure. Inside a world like Gliese 436b, Ice 7 is not a laboratory flicker. It is geography, a permanent stratum thousands of kilometers thick, as ordinary there as granite is here. There is a satisfying symmetry in how this world's biography was assembled, because it bridged the 2 great eras of planet hunting. Its 2004 discovery by radial velocity caught the wobble and gave the mass. Its 2007 transit, caught by a Belgian-led team using in part a modest 60-centimeter telescope, gave the size. And the transit nearly went unlooked for, because the odds of any given planet's orbit slicing across our exact line of sight are small, a few % for a world this close to its star. The team checked anyway, on the reasonable principle that cheap observations of interesting stars are never wasted, and the star dimmed on schedule, and a Neptune became, overnight, a measurable object with a density, an interior, and a story. It remains one of the field's better lessons in luck, which is that luck in astronomy is mostly a decision to keep looking. Step back from the planet's interior, and its very existence in this orbit poses a question the field is still working through. When astronomers finally accumulated thousands of planets and sorted them by size and orbit, a strange emptiness appeared in the charts. Close to stars, on orbits of a few days, there are plenty of giant Jupiters and plenty of small rocky worlds, but almost no Neptunes. The region is called the Hot Neptune Desert, and it is thought to be a killing field, a zone where medium worlds are exactly wrong, too small to hold their atmospheres against the star's radiation, as the giants can, and not small enough to have been born airless and indifferent. Neptunes that wander in are stripped, planed down over eons into bare super-Earths. And yet Gliese 436b sits well inside the desert's borders, wearing its atmosphere, bleeding its trailing veil, enduring. Its dim, gentle red star is surely part of the answer, a weaker stripping engine than the hot stars that keep the desert empty elsewhere. But part of the answer may also be timing, that we have caught a traveler partway through the desert rather than a resident who can stay. On the longest timescales, the behemoth may be the visible signature of a world in the slow process of being planed down to its ice. Hold the image of the whole system for a moment, seen from a great distance, because it may be the strangest single picture this list has offered so far. A small red star, dim and patient, no wider than a modest fraction of our Sun. Around it, on a 2.6-day circuit, a dark Neptune passing over the star's poles rather than its equator, trailing a colorless banner of hydrogen 50 times wider than the star itself, a flag of escaping atmosphere streaming back along the orbit. Inside the planet, under a shallow envelope of gas, an ocean's worth of water standing as hot crystal, solid at 440 degrees, kept solid by nothing but weight. And somewhere farther out in the dark, unfound, the massive companion whose patient gravity is thought to have tipped the whole arrangement sideways. Nothing in that picture is hypothetical for effect. Every element is either measured or demanded by measurements. This is simply what is there, 32 light-years from the room you are sleeping in, around the kind of dim star nobody notices, in a system that would have been dismissed as fantasy by any astronomer who died before the millennium. Descend into it once, carefully, because this is a journey no probe will ever file a report on. You enter at the top of a warm hydrogen sky, the small red sun behind you, dim and gentle, its light the color of a fire's last hour. The gas thickens as you fall, pressure mounting in a long crescendo, warmth rising around you like ocean water. There is no surface to anticipate, no crust waiting to stop you. Instead, the transition arrives gradually, the atmosphere below compressing towards something denser, until at last you approach the mantle itself, and your lights find it, if anything here could survive to carry lights. A plain of ice reaching to every horizon, glowing faintly with heat, its surface polished and wrong, hot to a degree no glacier could imagine, 400 degrees and solid, groaning under pressures that reforge water into mineral. Above you, kilometers of amber sky. Below you, thousands of kilometers of white crystal that has never once been cold. It would be among the quietest places in the universe, and among the most alien, and it is built entirely out of the most familiar substance you own. The eccentric orbit deserves one more sentence of respect, because the strangeness hides in how reliably it should not exist. Tides are the most patient force in astronomy. Give them a close orbit and a few 100 million years, and they circularize it, as dependably as friction stops a swing. Gliese 436 is not young. The system's age is measured in billions of years, time enough for tides to have done this job many times over. Yet the orbit remains visibly out of round, which means it is being actively maintained, stirred fresh faster than the tides can smooth it. Somewhere in the dark of that system, patient gravity is working against patient gravity, and has been for eons, and only one side of the argument has ever been photographed. The next world, at least, can be summed up in a single plain sentence. It is the darkest planet human beings have ever measured. Number 7. The darkest planet ever measured. Think about how black the blackest thing you have ever seen actually was. Fresh asphalt on a summer road reflects about 4% of the light that strikes it. A lump of coal manages around 4 to 5%. Black acrylic paint, the kind used to darken theatre walls, sits near 5%. Even the things our language treats as the definition of darkness are, measured honestly, faint mirrors. They all hand a little light back. 750 light-years away, in the constellation Draco, there is a planet that makes all of them look polished. It is called TRES 2b, and it reflects less than 1% of the light its star delivers. 99% and more of everything that touches it is swallowed. It is the darkest planet ever measured, darker than coal, darker than paint, darker than the road, a world-sized absence hanging in orbit around a star very much like our own sun. The planet's discovery was almost humble. TREES-2b was found in 2006 by the Transatlantic Exoplanet Survey, a project whose entire hardware budget would disappear into the parking lot fund of a major observatory. The survey used a network of 3 small telescopes in California, Arizona, and the Canary Islands, each with a lens about 10 centimeters across. That is smaller than a dinner plate. It is the class of instrument a dedicated hobbyist might keep in a spare room. Pointed at the right patch of sky for long enough, those little lenses caught a sun-like star dimming by a little over 1% every 2.5 days, the shadow of a giant planet crossing its face. The planet turned out to be a hot Jupiter, about 1.2 times Jupiter's mass, on an orbit lasting 2.47 days. For a few years, TREES-2b was simply one more entry in the growing catalogue of roasting giants. Then it got lucky in the way that matters most in astronomy. It happened to sit inside the patch of sky assigned to NASA's Kepler Space Telescope, which launched in 2009 to stare, unblinking, at 150,000 stars at once. TREES-2b was in the net, and it was recatalogued under a second name, Kepler-1b, the first previously known planet on Kepler's books. Which means the darkest world we know of was watched, continuously, by the most precise, light-measuring instrument humanity had ever put in space. That precision is what made the darkness measurable, and the measurement is a story in itself. In 2011, 2 astronomers, David Kipping and David Spiegel, realized they could use Kepler's data to weigh the planet's reflected light. As TREES-2b circles its star, it shows phases, exactly as our moon does. When it is off to one side of the star, we see half its day side. When it is about to pass behind the star, we see nearly all of its lit face. If the planet reflects any light at all, the total brightness of the system should rise and fall, very slightly, on the rhythm of the orbit. The operative words are very slightly. The signal Kipping and Spiegel went looking for was a brightening and dimming of about 6 parts per million. 6 millionths. To put that in human terms, imagine a stadium lit by 1 million identical floodlights, and imagine trying to notice from across a city that 6 of them had been switched off. Kepler noticed. The phase signal was there, but it was almost nothing, far fainter than any reflective planet could produce. The mathematics closed around a stark conclusion. The geometric albedo of TREES-2b, the fraction of light it reflects, is less than 1%. The obvious question is what a planet has to be made of to swallow light this thoroughly, and the honest answer is that astronomers are still not entirely sure. Part of the explanation is about what TREES-2b lacks. Jupiter is bright because it is cold enough to wear decks of ammonia ice clouds, and clouds are mirrors. TREES-2b orbits its star at about 1/10 of Mercury's distance from the Sun, and its day side runs near 1000 degrees Celsius. At that temperature, bright clouds cannot condense. The planet is denied a mirror. What its atmosphere holds instead is a set of aggressive light absorbers. Vaporized sodium and potassium, both of which drink visible light greedily, and possibly gaseous titanium oxide, a molecule that absorbs across broad stretches of the spectrum. An atmosphere loaded with absorbers and stripped of clouds becomes something close to a one-way door for photons. Light goes in, rattles around, is absorbed, and its energy is kept as heat. And yet even that may not be the whole answer. When theorists build model atmospheres out of sodium, potassium, and titanium oxide at these temperatures, they can get a planet very dark, but they struggle to get it quite this dark. The models keep wanting to hand back a stray % or 2 of light, and the planet refuses to hand back even that. Something about TREES-2b's chemistry or clouds, or the absence of them, is still missing from the equations. The darkest planet we know of is dark for reasons we can only mostly explain. On this list, that has a familiar sound to it, and the sound will get louder as the numbers get smaller. Here is the detail that turns this world from a curiosity into something stranger. A planet that absorbs 99% of a star's light cannot simply keep the energy forever. It must glow. All that swallowed starlight becomes heat, and a body at 1000 degrees Celsius radiates, faintly, in the dark red. Up close, Tres 2b would not look like a hole in space. It would look like an ember. A sphere larger than Jupiter, so black it would be invisible in reflected light, smouldering from within, a dim red furnace light, breathing out of its own cloudless depths. Imagine descending into it. You fall out of hard starlight into an atmosphere that eats your shadow first, because there is nothing below to catch it. The light around you does not fade the way evening fades. It is subtracted, wavelength by wavelength, until the star behind you is a memory, and your instruments insist, impossibly, that the air itself is black. There is no surface coming, because this is a gas giant, only depth. And then your eyes adjust, and you realize the darkness below you is not complete after all. The depths below are glowing. A red so faint it is less a light than a temperature you can see, rising from everywhere beneath you at once, the planet's own stored starlight coming back out of it a century late, in the wrong color. You are falling through the inside of an ember the size of a world, and the only illumination for 1 billion kilometers in any direction is the heat of everything this planet has ever swallowed. There is a legitimately unsettling thought buried in this world, and it is worth saying plainly, calmly, before we move on. We found Tres 2b because it happens to cross its star, announcing itself in silhouette every 2.5 days. Had its orbit been tilted a few degrees differently, it would transit nothing, reflect nothing, and reveal nothing. A planet like this, viewed without a transit, is very close to unobservable, which invites a simple piece of arithmetic. The galaxy contains hundreds of billions of stars, and we now know that planets outnumber them. Some fraction of those planets, orbits tilted askew, wrapped in absorbing skies, are simply dark. The night sky the listener carries in memory is not a complete inventory. It is the bright minority. Space is not only full of things too far away to see, it is full of things that are close enough and dark enough that seeing was never on offer. Tres 2b sits at number 7 rather than deeper on this list because, in the end, its strangeness is a matter of degree. It is a hot Jupiter, a familiar category, pushed to an extreme value of a familiar property. The worlds ahead of it are stranger in kind, but it leaves us with the purest single image this list will offer. Somewhere in Draco, right now, an ember the size of Jupiter is circling a yellow star every 2.5 days, swallowing its light, glowing the color of a dying coal, and it took the finest photometer humanity ever built to prove it was more than a shadow. The instrument that made the measurement deserves its portrait, because nothing about this discovery works without it. The Kepler Space Telescope was the culmination of one man's 4-decade insistence. William Barucki, a NASA scientist who had worked on heat shields for the Apollo program, began proposing a space-based transit-watching photometer in the 1980s, and was rejected repeatedly on the grounds that the required precision was impossible. He kept refining the proposal for the better part of 20 years until it flew in March of 2009. The finished spacecraft did exactly one thing supremely well. It stared at a single field of 150,000 stars in Cygnus and Lyra, without blinking, for years, measuring each star's brightness to a precision of tens of parts per million. That precision was meant for catching the shadows of Earth-sized planets. But precision is a general-purpose gift. Handed a hot Jupiter like Tres 2b, Kepler could go beyond detecting the planet's shadow and read the planet's own faint shine, the 6 parts per million breathing of its phases. It is worth being plain about what that means. The darkness of this world was measured by an instrument designed for a different job, wielded by 2 astronomers who saw that the data could answer a question nobody had thought to schedule. A great deal of what we know about the universe arrived exactly this way, in the margins of missions, by people paying closer attention than the plan required. For calibration, it helps to place TRES 2b on the full shelf of cosmic reflectivity, because the shelf is wider than intuition expects. At the bright end sits Enceladus, the small icy moon of Saturn, whose fresh snow surface bounces back nearly all the light it receives, close to a perfect mirror. Venus, wrapped in sulfuric acid clouds, reflects about 3/4 of incoming sunlight, which is why it owns our evening sky. Earth returns about 30%. Our own moon, which looks brilliant on a clear night, is actually surprisingly dark, reflecting about 12%, roughly the reflectivity of worn asphalt, luminous to us only because it stands against black space and near a bright sun. Jupiter manages around half. And then, far below the coal and the paint and the asphalt, below every planet and moon in our solar system's inventory, sits TRES 2b at less than 1%. There is one caveat that keeps scientists honest here. Human engineers have, in laboratories, produced materials even darker, forests of carbon nanotubes that swallow more than 99.9% of light, coatings so dark the eye reads them as holes in the world. So the universe has not beaten us at darkness in absolute terms. What it has done is manufacture that darkness at planetary scale, casually, out of hot gas and alkali metals, and hang it around a yellow star as if it were nothing special. Our darkest material is a coating measured in centimeters. Theirs is a weather system the size of Jupiter. There is also a gentle scientific afterword to the ember glow, because the physics of glowing is one of the oldest and most reliable in the book. Any object above absolute zero radiates, and as its temperature climbs past roughly 500 degrees Celsius, that radiation crosses into the visible, beginning with a dim red the eye can catch in a dark room. Blacksmiths have navigated by this for millennia, reading the temperature of iron off its color, from first faint red through orange toward white. TRES 2b's day side, near 1000 degrees, sits comfortably in the orange-red range of that ancient scale. So its glow is not exotic. It is the same glow as a horseshoe pulled from the forge, obeying the same law, scaled to a sphere 140,000 kilometers across. Astronomy keeps doing this, taking the physics of the workshop and the kitchen and stretching it over objects the size of worlds, and the stretching never quite stops feeling improper. A planet should not be describable with the vocabulary of a forge. This one is. The planet also carries a small historical distinction that says something about how fast this field has moved. When Kipping and Spiegel published its darkness in 2011, the very idea of measuring an exoplanet's reflected light was at the bleeding edge, and TRES 2b became the standard example, cited in classrooms and textbooks as the darkest world known. In the years since, the technique has matured. Other pitch-dark hot Jupiters have joined the shelf, and one of them, an egg-shaped world with far worse problems than darkness, is waiting for us at number 2 tonight. But the ranking has held remarkably well. Nearly a decade and a half of increasingly precise photometry has failed to produce a planet convincingly darker. In a discipline where records usually fall every few seasons, the ember of Draco has kept its dark crown. For a sense of what such a world would do to a familiar sky, run the standard thought experiment and place TRES 2b where Jupiter rides in our own system. Jupiter, at its brightest, is the 4th brightest object in Earth's sky, an unmistakable lantern that has anchored calendars and navigation for millennia, shining by bounced sunlight. Swap in the ember world, and the lantern goes out. At less than 1% reflectivity, the planet would dim below naked eye visibility, an absence patrolling the ecliptic, findable only by the stars it briefly blots out as it passes. Astronomy on such an Earth would have discovered its largest planet not as a light but as a wandering hole in the sky, a silhouette hunting through the constellations. The ancients would have told very different stories about that. The planet's two names tell a small story about how fast its era moved. It was born Tres 2b, the second catch of the Transatlantic Exoplanet Survey, one of a modest family of worlds found by that pioneering little network before larger projects absorbed the frontier. 3 years later, Kepler's field of view happened to cover it, and the mission's catalogue, needing a numbering scheme, began with the planets already known inside its stare. So the darkest world became Kepler 1b, the first entry in the ledger of the most productive planet-finding mission in history, a ledger that would eventually run past 2,700 confirmed worlds. There is something fitting in the coincidence. The catalogue that would reveal the galaxy's planetary abundance opens, at entry number 1, with a planet that swallows light, as if the ledger itself began by noting that most of what the universe contains does not announce itself. The darkness measurement, it should be said, has aged well. Later analyses of additional years of Kepler photometry re-derived the phase signal with more data and better methods, and the planet stayed dark, its reflectivity pinned at the bottom of the scale. That endurance matters, because extraordinary measurements at the edge of an instrument's precision sometimes soften under re-examination, and this one did not. The techniques pioneered here, meanwhile, have become standard equipment. Phase curve photometry now routinely maps the reflectivity and heat of worlds across the catalogue, building albedo tables the way an earlier astronomy built star charts. The Ember of Draco was where the method proved it could weigh almost nothing and be believed. From the darkest world we know, the list turns next to one of the most vividly colored. The next planet is a rich cobalt blue, the blue of postcard oceans, and it would look almost like home, right up until the weather report arrives. Number 6, the planet where it rains, molten glass. If you could hold up a photograph of the 6th planet on our list, taken from a distance, most people would smile at it. The planet is blue. Not a moody grey blue, not a suggestion of blue, but a rich, saturated cobalt blue, the blue of Earth, in the famous photographs taken from the Moon. It is the most familiar color in the solar system, the color we put on classroom globes and mission patches, the color that means water, weather, home. In the entire catalogue of thousands of known worlds, this was the first planet beyond our solar system whose true color humanity ever measured. And the color is a lie so complete it approaches poetry. The planet is HD 189733b, and it orbits an orange dwarf star just 64 light-years away, in the small northern constellation Vulpecula, the little fox. In the sky it sits close beside the Dumbbell Nebula, a target beloved by amateur astronomers, and the star itself is bright enough to find with binoculars from a dark backyard. As exoplanets go, this is a next-door neighbor. The galaxy is 100,000 light-years across, and this world is 64 light-years up the street. It was discovered in 2005 by a team led by François Bouchy at the Haute-Provence Observatory in the south of France, and it won the astronomical lottery twice at birth. First, it transits, crossing the face of its star every 2.2 days, which means astronomers can watch starlight filter through its atmosphere. Second, its star is unusually bright and unusually close, which means there is plenty of that light to study. Those two facts together made HD 189733b the single most examined planet of its generation. For 2 decades, nearly every new technique in the young science of exoplanet atmospheres was tested here first. It is the laboratory planet the world science practices on, and the file that practice produced reads like a weather report written for another universe. Start with the temperature. The planet is a gas giant, slightly heavier than Jupiter, parked 25 times closer to its star than the Earth is to ours. Its dayside runs near 930 degrees Celsius, roughly the temperature of flowing lava. In 2007, a team led by Heather Knutson used the Spitzer Space Telescope to track the planet's heat through a full orbit and produced the first crude temperature map of a world beyond the solar system, a genuine milestone in the history of maps. Cartography, which began with coastlines sketched from ship rails, had reached another star, and the first thing it recorded there was a hemisphere hot enough to glow. Now add the wind. By tracking sodium absorption racing through the atmosphere, astronomers clocked winds on this planet at up to 8,700 kilometers per hour. Numbers that large stop meaning anything without a comparison, so here are 3. That is over 2 kilometers every second. That is roughly 7 times the speed of sound. A parcel of that wind could cross the continental United States in about half an hour. The strongest hurricane ever recorded on Earth would register on this planet as a stillness between gusts. And now add the rain, because it is the rain that makes this world famous. The blue color, measured by the Hubble Space Telescope in 2013 from the light the planet reflects, does not come from oceans. There are no oceans. It comes from the clouds themselves, and the clouds are not water. At 900 degrees, the condensable material in this atmosphere is rock. The cloud decks of HD 189733b are built from microscopic droplets of silicate, which is to say, molten glass. Those droplets scatter blue light the same way the molecules of Earth's atmosphere scatter blue light to make our sky, and so the whole planet wears the color of a swimming pool. When the droplets grow heavy enough to fall, they fall into winds moving 7 times the speed of sound. The rain on this planet does not fall down in any meaningful sense. It falls sideways. Horizontal rain at 2 kilometers per second, and every drop of it is glass. Let the picture assemble itself for a moment. A sky of postcard blue, clouds with the sheen of stained cathedral windows, and moving through it, permanently, a wind that would strip the surface off a mountain, carrying a horizontal weather of molten droplets that would sandblast anything solid into vapor. It is the most vivid, most visitable-seeming hostile place in the entire exoplanet catalogue, the world where our instruments have painted the fullest picture, and every stroke of that picture is fatal. Then, in the summer of 2024, the James Webb Space Telescope added a detail so vivid it belongs in fiction. Webb's spectrographs, passing the starlight that grazes through the planet's atmosphere during transit, detected hydrogen sulfide. That is the molecule of rotten eggs, of struck matches, of sulfur springs. It was the first time hydrogen sulfide had ever been identified on any planet outside the solar system, and it came bundled with clean detections of water vapor, carbon dioxide, and carbon monoxide. The finding matters scientifically because sulfur is a bookkeeping element, a tracer that records how a planet was assembled. But it matters to the imagination for a simpler reason. We now know what this planet would smell like. Blue skies, glass rain, and the reek of sulfur. The universe filled in a sense we never expected to use at 64 light-years range. The planet's resume of scientific firsts runs longer than its forecast. It was among the first exoplanets to have water vapor firmly identified in its air. In 2008, it became the first exoplanet with a confirmed detection of carbon dioxide. Its sodium was spotted from telescopes on the ground, a proof that even Earth's turbulent atmosphere could be beaten by clever technique. Astronomers have watched its upper atmosphere boiling away under stellar radiation, a slower, gentler version of the great escaping plume we met at Gliese 436b. They have even caught its star in the act of flaring directly onto it. The star is a magnetically restless orange dwarf, and the planet orbits close enough that every stellar tantrum arrives at point-blank range, lashing an already superheated sky with X-rays. There is one more first hiding in this system, and it is quietly beautiful. Because the star is so bright and the planet so well placed, HD 189733b is where astronomers refined the trick of studying a planet they cannot see as a disk at all. Every fact in this item, the temperature map, the wind speed, the color, the smell, was extracted from a single point of light that never once resolved into an image of the planet itself. The whole biography was read from flickers and tints. It is worth remembering, as this list moves toward worlds known only from shadows and wobbles, that this is what patient measurement can do with almost nothing. Given 1 point of light and 20 years, science produced a weather report, a map, a color swatch, and a smell. The open questions here are the quiet kind. Astronomers still work on how glass clouds organize themselves in supersonic wind and on how much total atmosphere the planet has surrendered to its star over the eons. But HD 189733b is, by the standards of this list, a solved world, and that is precisely why it sits at number 6. Its strangeness is not a mystery. It is a completed portrait whose every detail happens to be lethal. The worlds remaining on our list get progressively less explained from here. Before we move inward, hold on to this planet's central lesson. Blue does not mean home. The most earth-colored world in the catalogue is a furnace wrapped in glass storms and sulfur. In the exoplanet era, familiarity is a costume that worlds wear over physics we are only beginning to understand. The technique that read this planet's air deserves a clear picture in your mind, because it is the master key to half the discoveries in this countdown. When HD 189733b crosses its star, the planet's opaque body blocks a small, fixed fraction of the starlight. But wrapped around that body is a thin shell of atmosphere, and starlight grazing through that shell does not pass untouched. Every gas has an appetite for particular wavelengths, as individual as a signature. Sodium bites 2 narrow lines out of the yellow. Water drinks broadly in the infrared. Carbon dioxide takes its share elsewhere. So during transit, the star appears very slightly larger, meaning dimmer, at exactly the wavelengths the planet's air is eating, and very slightly smaller at wavelengths it lets pass. Compare the star's spectrum during transit against its spectrum alone, and the difference is a chemical inventory of a sky 64 light-years away. The differences involved are tiny, parts in 10,000, which is why this planet's pairing of a bright star with a large atmosphere made it the field's favorite proving ground. The first confident detection of sodium here was made in 2007 from a telescope standing on the ground in Texas through the churn of Earth's own weather, an achievement the field had widely assumed would require space. The planet kept rewarding whoever tried the next impossible thing. Its scientific biography since then reads like the syllabus of an entire discipline. In 2007, the first thermal map, which revealed one more detail worth savoring, that the hottest point on the planet is not the point facing the star. The ferocious winds drag the heat downstream, displacing the planet's thermal noon eastward by hundreds of kilometers, exactly as atmospheric models predicted a wind-swept locked world should behave. In 2008, the first detection of carbon dioxide on any world beyond the solar system. In the years after, astronomers watched the planet's extended upper atmosphere in ultraviolet as it boiled off into space, and caught the loss rate surging after the star unleashed an X-ray flare, cause and effect between a star's tantrum and a planet's thinning air, observed across interstellar distance. In 2018, astronomers found helium streaming from its upper atmosphere, the first clear helium detection in any exoplanet's air, made at a wavelength physicists had predicted decades earlier would someday serve exactly this purpose. Paper by paper, this one world taught the community the entire craft it now applies across the galaxy. It is worth dwelling briefly on the star as well, because the star is a character in this weather, not a backdrop. HD 189733 is an orange dwarf, cooler and smaller than our Sun, but young and magnetically restless, its surface strung with star spots and prone to flares. The planet orbits at point-blank range, and so it lives inside its star's weather as much as its own. Stellar storms that would need days to reach Earth arrive there in hours. Charged particles rake its upper atmosphere. Each flare heats and inflates the planet's outer air, quickening the leak that ultraviolet astronomers measure. Over billions of years, this arrangement is a slow contest between the planet's gravity and the star's temper, and the honest projection is that the star wins eventually, in the sense that the planet's hydrogen envelope thins age by age. But the giant is massive enough that the loss stays cosmetic on any timescale that matters. Like the bleeding Neptune at number 8, this world can afford its wound. One more perspective earns this planet its farewell. Almost everything humanity knows about it, the blue, the winds, the map, the sodium, the sulfur, was extracted without ever resolving the planet as anything but a single point of light blended with its star. And yet the file on this point of light now runs to hundreds of published studies, thousands of hours of telescope time across a dozen observatories in space and on the ground, a 2-decade collaborative portrait assembled by people spread across every continent, most of whom never met. If some observer out there ever undertakes the reverse project, pointing patient instruments at our Sun and teasing the Earth's story out of flickers and tints, they would find their weather report far milder and the substance of the exercise identical. Curiosity aimed steadily at a dot for 20 years. That is what the strangeness of the universe reliably meets on our side of the telescope, and it is a fair trade. The planet's discovery even carries a small charm of location. Its star sits, by pure line-of-sight coincidence, close beside the Dumbbell Nebula, the glowing shroud of a dead star and one of the most photographed objects in amateur astronomy. Backyard astronomers imaging that famous nebula have for decades been unknowingly photographing the host star of the most studied planet in the sky, an unremarkable orange point in the corner of 1,000 souvenir pictures. Astronomy does this often, hiding its most significant addresses in plain sight, filed among the scenery. One more of this planet's firsts deserves its story told properly, because at the time it landed like a thunderclap. In 2008, astronomers using an infrared camera on the Hubble Space Telescope reported carbon dioxide in the planet's atmosphere, the first detection of that molecule beyond the solar system. The reason the community sat up was not the gas itself, which any hot Jupiter might carry. It was what the detection certified about the method. Carbon dioxide is one of the marker gases in the search for living worlds. Part of the chemical shortlist astronomers hope one day to read in the air of a small temperate planet. Finding it on a scorched giant proved the reading itself could be done, that our instruments could reach across light years and identify, unambiguously, a specific triatomic molecule in alien air. Every atmospheric biosignature hunt now underway, on quieter and more hopeful worlds, descends from proofs of concept performed on this furnace. Hold the descent in your mind once, before we leave, the way the instruments describe it. You fall out of space into blue. From above, the planet is serene, a marble of rich cobalt, and the first kilometers of descent almost keep the promise. Sky lightening around you, a blue overhead that any Earth morning could have supplied. Then the wind takes you. Not a gust, a current, a permanent planetary river of air moving 7 times the speed of sound, and you move with it, because nothing resists it. In the cloud decks, the light turns silver and wrong, and you see the rain at last, glittering threads of molten glass streaking past horizontally, each droplet a bead of liquid stone drawn into a line by speed. Lightning, if it is there, arrives sideways. Below you, the glow begins, the dayside's furnace floor shining up through the storm like a city under fog. It is beautiful the entire way down. That is the detail the numbers keep insisting on. Nothing about this place pauses being lethal, and nothing about it pauses being blue. 64 light-years is close, as the galaxy measures things. The next planet on our list is nearly as close, and it may be made mostly of the most familiar substance there is. It may be a world of water, and every drop of that water is wrong. Number 5. The steam world wrapped in a mirror. Some worlds are strange because of what we found there. The 5th planet on our list is strange for the opposite reason. For more than a decade, it was the most famous planet in the galaxy for refusing to answer questions. Astronomers aimed the best instruments humanity has ever built at it, over and over, mission after mission, and the planet handed back nothing. A flat line. A shrug. It became the exoplanet community's politest running joke and deepest frustration, the world that would not talk. And when it finally did talk, in the era of the James Webb Space Telescope, its answer was stranger than anyone's guess. The planet had spent all those years wrapped in a mirror. The world is called GJ 1214b, and it orbits a small red dwarf star, 48 light-years away, in the constellation Ophiuchus. Its discovery, in 2009, is one of the great underdog stories in modern astronomy. It was not found by a space telescope or a mountaintop giant. It was found by the Mirth Project, an array of 8 14-inch telescopes, the kind of instrument a serious amateur might own, lined up on a hillside at the Whipple Observatory in Arizona under the direction of the astronomer David Charbonneau. The project's premise was elegant. Small red stars are so dim and so little that a modest planet crossing one blocks a meaningful fraction of its light, a signal big enough for small telescopes to catch. Point cheap hardware at humble stars and let the geometry do the work. Within its first full season, the strategy landed a planet that would occupy the field for 20 years. GJ 1214b measures about 2.7 times the radius of the Earth and carries about 8 times the Earth's mass. Those two numbers, taken together, are the door into everything strange about it. The planet is far too light to be a ball of rock and iron at that size, and far too heavy and small to be a gaseous world like Neptune. Its density falls into a gap where our solar system offers no example at all, a category of planet the Sun simply never made. When theorists solved for what could produce that density, the leading answer was almost disarmingly simple. Water. Not a rocky planet with oceans, but a planet whose very substance is water, perhaps a large fraction of its total mass, wrapped around a core of rock. For comparison, all the oceans, ice caps, rivers, and clouds of Earth together amount to about 0.02% of our planet's mass. Earth, the blue marble, is bone dry. GJ 1214b may be the real thing, a world where water is not a feature on the surface, but the planet itself. But water on this world would follow none of the rules the word brings to mind. The planet orbits its red star every 38 hours, close enough that its atmosphere simmers around 280 degrees Celsius. There is no shoreline down there, no surface at all in the familiar sense. Descend into GJ 1214b and you pass through thousands of kilometers of superheated steam, pressed gradually denser and hotter, until the distinction between atmosphere and ocean stops meaning anything. Deeper still, pressure does to water what we watched it do inside Gliese 436b, forcing it into hot, solid phases, exotic ices that no cold ever touched. And in between, physicists expect stranger states yet. Supersonic water, in which the oxygen atoms lock into a rigid lattice, while hydrogen pours through that lattice like a liquid flowing through scaffolding, a substance that is simultaneously solid and molten. Possibly plasma water, compressed and heated until the molecules themselves shred apart. These states of water are not fiction. Laboratories on Earth have created flickers of them for fractions of a second inside shockwave experiments and diamond presses. On GJ 1214b, they may sit in permanent layers, planetary strata made of water, wearing costumes chemistry never shows us. That was the theory, at least. Proving any of it required reading the planet's atmosphere, and this is where GJ 1214b turned legendary. The standard technique is transmission spectroscopy. When the planet crosses its star, a thin ring of starlight filters through its upper atmosphere, and every molecule in that air steals its own signature wavelengths. Read the stolen colors and you read the recipe. The technique had worked beautifully on the glass rain world one item ago. So astronomers pointed Hubble at GJ 1214b and measured. The spectrum came back flat. No water signature, no methane, no anything, just an even, featureless line across every wavelength. They measured again, deeper. Flat. Campaign after campaign, year after year, the most studied small planet in the sky produced a spectrum with the informational content of a drawn curtain. A flat line, though, is itself a clue. Only one thing produces it. Something opaque floats high in that atmosphere, a deck of haze or cloud, so complete and so elevated that starlight never reaches the gases below. The curtain was real, a global veil wrapped around the entire planet, hiding every molecule underneath. For years, that was the state of knowledge. We had found a possible water world, and it had, in effect, declined to comment. The James Webb Space Telescope finally broke the silence, and it did so by changing the question. Rather than reading starlight through the atmosphere's edge, a team used Webb's mid-infrared instrument in 2023 to track the planet's own heat through an entire orbit, watching its day side and night side swing past in turn. The measurement produced two revelations. The first was expected in kind, if not degree. The atmosphere is not lightweight hydrogen fluff. It is heavy, dense with molecules far weightier than hydrogen, consistent with an air rich in steam or carbon dioxide, or both, enriched in heavy elements at least 100 times beyond the composition of the sun. A thick, hot, metal-rich sky over a possible ocean planet interior. The second revelation was the surprise. The planet is shiny. Working out the energy budget, the team found GJ 1214b reflects roughly half the starlight that strikes it, a figure later refined to around 40%, and either number is remarkable. Earth, with its bright clouds and ice caps, reflects about 30%. The haze that spent a decade humiliating our telescopes is not a grey smog. It is one of the most reflective planetary veils ever measured on a small world, a bright shell bouncing starlight back into space. 2 items ago, we met the darkest planet ever measured, a world that swallows more than 99% of the light it receives. Here is its opposite pole, a steam planet wrapped in a mirror, and it sits in the same 10-item list because the galaxy apparently stocks both extremes. What exactly the mirror is made of remains open. The leading candidates are hazes built by chemistry high in the atmosphere, particles forged when stellar radiation works over a soup of heavy molecules. Laboratory teams have been cooking candidote hazes in chambers, testing which recipes turn out bright instead of sooty. There are stranger wrinkles too. The planet's night side runs warmer than the simplest models predicted, hinting at winds ferrying heat around the globe beneath the veil, an entire hidden weather system doing its work behind the mirror. And the deepest question, whether this world truly is a water planet, or instead some miniature gas world in disguise, is still not fully closed. The evidence leans wet. The verdict is unsigned. There is something almost fable-like about this planet, and it is worth letting the shape of the story land. The most ordinary substance in your life, the thing in your glass on the nightstand, may be the entire identity of a world 48 light-years away, existing there in forms no human hand will ever touch, under a sky that spent 20 years refusing to be red, behind a veil that turned out to be silver. Water, the most familiar thing there is, wearing the galaxy's best disguise. The category this planet belongs to carries a significance that reaches far beyond one strange world, and it deserves a moment of plain statement. When the Kepler mission finished its census of the galaxy's planets, the single most common size class it found was exactly this one, worlds larger than Earth and smaller than Neptune. The galaxy manufactures these in-between planets in greater numbers than any other kind, and our solar system contains none. The most typical planet in the Milky Way is a category of world we cannot visit, cannot photograph up close, and cannot check against a local example. Everything we learn about the galaxy's most common product has to be learned the hard way, at light years of range, from worlds like GJ 1214b. That is why a decade of flat spectra stung as much as it did. The planet was not merely keeping its own secrets. It was keeping the secrets of the most numerous planetary family in the galaxy, the family our own system inexplicably skipped. The scale of the effort spent against that veil is worth recording, because it measures how much the answer mattered. In the early 2010s, astronomers committed enormous stretches of Hubble Space Telescope time to this one world, eventually stacking more than a dozen transits into a single combined measurement of unprecedented delicacy. The result, published in 2014, was a spectrum flat to within 30 parts per million, the most precise flat line in the history of the field. It ruled out every cloudless atmosphere on the menu, cloud-free hydrogen, pure steam, all of it, and established the veil as real, high, and complete. There is a special kind of scientific achievement in measuring nothing this well. The 2014 flat line is quietly one of the most informative null results in astronomy, because it transformed the planet's silence from a frustration into a fact with hard edges, a measured, bounded, undeniable curtain that any future theory would have to produce on demand. The 2023 thermal measurements added one more finding that rarely makes the headlines, but may be the most consequential of all. The planet's night side, the hemisphere turned permanently away from its star, is far warmer than an airless or thin-aired world could ever be. Heat is plainly being carried around the planet in bulk, which means winds, global circulation, an atmosphere thick enough to work as a planetary heating system, ferrying energy from the day side around to the dark. Beneath the mirror, in other words, there is weather, an entire circulating climate operating under a lid that no outside eye has ever penetrated. Climate modelers have begun building simulated versions of it, hot, steam-rich atmospheres spinning on a 38-hour day, and the simulations produce jet streams and condensation and structure, an invisible meteorology running its systems in the dark, 48 light-years away, entirely indifferent to the fact that it cannot be watched. Let the double image of this world settle before we leave it, because the two halves make one of the stranger portraits in the catalogue. From outside, GJ 1214b is a bright, sealed, silver-hazed sphere, among the most reflective small worlds ever measured, circling its dim red star every day and a half, like a ball bearing turning around a coal. From inside it is depth without flaw, steam pressing down into hot exotic ice, water conducting itself in ways our language has no household words for, wrapped in winds no one will ever feel. Between those two descriptions sits the veil itself, one of the great unopened envelopes in modern astronomy. Instruments now flying, and instruments still on drawing boards, will keep working at the seam. The reasonable expectation is that some year fairly soon, the mirror world will finally give a chemical answer, and the galaxy's most common kind of planet will begin, at last, to explain itself. The night this planet was found makes a fitting story for the strategy that found it. The Earth telescopes ran automatically, cycling through a list of 2,000 nearby red dwarfs, taking a quick exposure of each and moving on, software flagging anything that dimmed. In May of 2009, the system flagged the star GJ1214, and the flag was nearly discarded because the star is a jittery little thing whose ordinary flickering had cried wolf before. A graduate student on the project, Zachary Berta, noticed the dip's shape looked cleaner than the star's usual noise and pushed for a closer look. The follow-up caught the transit again, on schedule, and the jittery star's flag became one of the signature discoveries of the decade. The margin between a landmark planet and a deleted data point was one student deciding a wiggle deserved a second glance. It helps to hold the scale of this system honestly, because it is easy to imagine exoplanet systems as grand. GJ1214, the star, is a fifth the size of our Sun, with less than 1% of its brightness, a dim red coal that would need to be seen from closer than Mercury to look as bright as our daylight. The planet circles it at a distance of just 2 million kilometers, 5 times closer than Mercury hugs the Sun. The entire orbit, the whole year of this world, would fit comfortably inside the Sun itself, with room to spare. Miniature star, miniature orbit, and in the middle of it, a planet from the galaxy's most common and least understood family, running its 38-hour years by the billion, while its silver veil holds. The larger family portrait has one more feature worth knowing, because GJ1214b sits right at its most interesting border. When astronomers finally had thousands of small planets to sort, they noticed the sizes do not spread smoothly. Planets bunch at about 1.5 times Earth's size, and again at about 2.5 times, with a marked scarcity in between, a trough in the statistics now called the radius valley. The interpretation, worked out over the past decade, is elegantly brutal. Worlds are commonly born with thick hydrogen envelopes, but close to a star, radiation strips those envelopes away. Planets that lose the envelope shrink to the smaller peak, bare rocky cores. Planets that keep it hold the larger size. The valley between is the population that could not decide, worlds caught mid-stripping. On one side of the valley stand the super-Earths, on the other the sub-Neptunes, and the difference between them is often nothing but the keeping or losing of a sky. GJ1214b stands firmly on the keeping side, its heavy, mirror-wrapped atmosphere intact, which is precisely why it has so much to teach. It is a surviving example of the very possession, a thick, volatile envelope on a small world, that the galaxy spends so much of its energy confiscating. Patience, in the end, is the planned strategy for this world, and the schedule is real. The James Webb Space Telescope continues to revisit it, each campaign chipping at the veil from a new angle. Later this decade, a European mission named Ariel is designed to survey the atmospheres of hundreds of transiting planets in assembly line fashion, building the first true chemical census of other skies, and haze-wrapped small worlds sit high on its docket. Ground-based giants now under construction, with mirrors tens of meters across, will add their weight. Somewhere in that pipeline, most astronomers expect, the silver world will finally speak. Until then, it keeps it standing as the galaxy's most eloquent refusal, the planet that taught an entire field the difference between measuring nothing and learning nothing, which turn out, done carefully enough, to be opposites. A planet that hides itself is strange. But at least a hidden world holds still while it hides. The next planet on our list does something more unsettling. It changes while we watch. And it may have no solid ground anywhere on its sunward face at all. Number 4. The planet whose year lasts 17 hours. We have now crossed the halfway point of this list, and it is worth pausing for one breath to look back down the slope. We began with a broken promise, a second Earth that turned out to be an oven with mail on the way. We met a giant that orbits backward under clouds of quartz, a world of ice that burns trailing a comet's veil, an ember-black planet that swallows its own daylight, a blue world of sideways glass rain, and a steam planet wrapped in a mirror. 5 worlds in, the rulebook we inherited from our own solar system is already in pieces. And the strangest half of the list is still below us. The 4th planet on our list is the one you can come closest to touching, and that is precisely what makes it the existential center of this countdown. Everything else tonight lives at distances that are really just arithmetic. This one has an address you can see. On any clear, dark night in the right season, walk outside and find the constellation Cancer, the faint crab that sits between the bright twins of Gemini on one side and the sickle of Leo on the other. Cancer is dim, easy to miss, a constellation most people have never consciously seen. But under a properly dark sky, away from city light, there is a star in it that you can find with your unaided eye. No telescope, no binoculars, just patience and a star chart. Astronomers catalogue it as 55 Cancri. It even has a formal name now, Copernicus. The light arriving at your eye from that star is 41 years old, which means, for many people listening tonight, it left the star around the year they were born. And circling that star, closer to it than anything in our solar system dares to orbit the sun, is a planet where a full year lasts 17 hours and 40 minutes. Sit with that number for a moment, because it rewrites a word you have used your whole life. A year is the planet's full journey around its star, the same journey that takes the Earth 365 days. On this world, the whole circuit is finished in less than a single Earth day. Begin an evening at home tonight, and by tomorrow afternoon, that planet has completed an entire year. In the time it takes you to sleep through one night, its year is nearly half over. A person who somehow lived 30 Earth years on that world would be more than 14,000 of its years old. Every birthday you have ever had, it has had 490 of them. The planet is 55 Cancri E, and it has been surprising astronomers for over 2 decades. It was discovered in 2004 by a team led by Barbara MacArthur, using precise radial velocity measurements anchored by the Hobby Eberly telescope in Texas. And even its discovery was strange, teased out of the wobbles of a star that hosts 5 known planets, one of the fullest planetary systems in the catalogue. There is even a second star in the family, a small red dwarf companion that orbits the whole arrangement from a great distance, so any sky on this planet holds 2 suns, one enormous and one faint. In 2011, astronomers caught 55 Cancri E transiting, and the geometry snapped into focus. The planet is about twice the width of the Earth, and about 8 times its mass, a dense, rocky super-Earth, a genuine relative of the ground you are lying on right now. And it orbits its sun-like star at 1/65th of the Earth's distance, 25 times closer in than Mercury. Numbers like that turn a rocky world into something the solar system never taught us to imagine. The day side of 55 Cancri E runs near 2,400 degrees Celsius. That is not volcano temperature. That is well past the melting point of granite, past iron, approaching the domain where rock does not merely soften, but flows freely and begins to evaporate. The planet is almost certainly tidally locked, one face pinned toward the star forever, and that face is not a landscape. It is an ocean. A hemisphere-wide sea of molten rock, glowing with its own light, with no coast on its sunward side, because there may be nothing solid there to make a coast out of. From that surface, if the word surface applies to the skin of a magma sea, the star would be a presence unlike anything in human experience. Our sun covers about half a degree of Earth's sky, the width of a fingernail at arm's length. From 55 Cancri E, its star sprawls across dozens of times that width, a dome of white fire occupying a great sector of the heavens, pouring down heat that keeps stone liquid the way our sun keeps water liquid. Hold your hand toward a bonfire and feel the skin of your palm tighten. Now let the bonfire fill a quarter of the sky. Picture drifting above that dayside for a moment, held safe by impossibility. Below you, a sea of incandescent rock rolls to the horizon in slow, heavy swells, orange-white and glaring, veined with darker currents where cooler stone folds under. There is no land to interrupt it, anywhere. The heat rising off the sea is a physical pressure against your skin, a hand pushing you upward. Above, the star does not sit in the sky the way our sun does. It occupies the sky, a white immensity you could not blot out with both fists, so bright the molten sea below is lit twice, once by the star and once by its own glow answering back. And at the edge of your vision, all around the rim of the world, a thin shimmer rises off the magma like heat off summer asphalt. That shimmer is the planet's atmosphere, and it is being breathed out of the rock itself, even as you watch. That shimmer is the discovery that made this planet an anchor on our list. In May of 2024, measurements from the James Webb Space Telescope settled a long argument and opened a stranger one. 55 Cancri has an atmosphere. Not a wisp of vaporized rock hugging the surface, which was one long-standing guess, but a genuine secondary atmosphere, apparently rich in carbon dioxide and carbon monoxide, wrapped around a rocky planet. It was the first time in history that an atmosphere had been confirmed on a rocky world outside our solar system, a milestone the field had chased for a generation. And it makes very little sense. This close to a star, an atmosphere should not survive. The star's radiation and wind should strip it away into space, on timescales that are, astronomically speaking, brief. Something is replacing the air as fast as the star steals it. The leading explanation is directly beneath the shimmer. The magma ocean itself is the lung. Gases dissolved in the molten rock bubble continuously out of the sea, exhaled into the sky, torn away by the star, and exhaled again. An atmosphere with a heartbeat, fed from below, spent from above, in permanent turnover. The planet does not have air the way Earth has air. The planet breathes. And then the story tilted from remarkable to genuinely strange, because the planet declined to stay consistent. Follow-up observations found the signals changing between visits. Carbon monoxide emission that was clearly present in one set of measurements weakened or shifted in another. The planet's brightness at given wavelengths refuses to hold steady. And this fits an older suspicion, because a decade earlier, the Spitzer Space Telescope had watched the planet's total heat output swing several-fold across just a few years, an enormous change for a solid world, with no accepted explanation. Astronomers now say out loud that 55 Cancri E appears to be variable, a planet observed in the act of being unstable. The candidate explanations are all dramatic. Volcanic outbursts on a scale Earth has never seen, veiling and unveiling the surface. An atmosphere that partially collapses and rebuilds itself in cycles. some rhythm of the magma sea that no one has modeled correctly yet. The honest label, once again, is unresolved. We have caught a planet changing, and we do not know why. For completeness, and because this list keeps its promises about honesty, we should visit the most famous claim ever made about this world. In 2012, a modeling paper made global headlines by proposing that 55 Cancri E might be a diamond planet. The argument ran through the chemistry of its star, which appeared rich in carbon relative to oxygen. A planet condensed from carbon-rich material would build its mantle not from silicate rock, but from carbon, and carbon at planetary pressures becomes diamond, entire continental layers of it. The claim was legitimate science, and it was also fragile. Within a year, other astronomers remeasured the star and found its carbon abundance had been overestimated. The diamond planet's foundation quietly dissolved. The idea survives in headlines to this day, but the honest status is contested and probably wrong. What is true is stranger in its own way. We genuinely do not know what the inside of this planet is made of, and every attempt to pin it down has slid off. A world 2 times the width of Earth, close enough to see its star with your naked eye, and its substance is still an open file. Here is why 55 Cancri E anchors the heart of this countdown. Every other planet tonight asks you to imagine somewhere unreachable. This one collapses the distance. The star is in your sky. You could stand in your yard tonight, in the cold, in your ordinary life, and hold your eye on a point of light whose planet finishes a year between your bedtime and your alarm, breathes an atmosphere out of a sea of molten stone, and visibly changes from one season of observations to the next, while the finest telescope ever built watches it happen. The strangest things in the universe are not somewhere else. Some of them are simply upstairs. The system this planet belongs to rewards a longer look, because 55 Cancri was a landmark address before this planet was even confirmed. It was among the very first stars found to host multiple planets, and today its known family numbers 5, spanning an architecture unlike anything at home. Innermost rides our subject, the 17-hour world. Farther out orbit 3 giants at various distances, and beyond them, at roughly Jupiter's distance from its star, a genuinely massive outer guardian about 4 times Jupiter's weight. 2 suns preside over the arrangement, the bright primary and a distant small red companion that circles the whole system more than 1,000 astronomical units away. Any inhabitant of this system, gazing from any of its worlds, would see a sky with 2 suns of wildly unequal rank and a procession of sibling planets. When the International Astronomical Union invited the public to help name exoplanet systems in 2015, this one received names honoring the history of the telescope itself. The star became Copernicus. Its planets took the names of the great instrument makers and observers, and the 17-hour world became Janssen, after a claimed inventor of the earliest telescopes. There is a fitting circularity in that. The world that has demanded more telescope time than nearly any rocky planet in the sky carries the name of the craft that made looking possible. The transit discovery in 2011 has a detail worth telling properly, because it shows how prediction works when a field matures. After years of radial velocity refinements, astronomers re-derived the planet's orbit and realized the odds of it transiting were substantial, and they knew precisely when any transit would have to occur. 2 space telescopes were duly aimed, and both caught the dip, a fingernail's shave of the star's light, arriving on schedule. The planet was not stumbled upon in silhouette, the way survey planets are. It was summoned into silhouette by arithmetic, told when and where to appear, and it appeared. In the years after, measurements even pulled out the planet's own infrared glow as it slipped behind the star, the first direct detection of light from any super-Earth, a thermometer reading taken across 41 light-years of empty space. Since then, 55 Cancri has effectively functioned as a stress test for every new generation of instruments, and it keeps returning the same verdict, which is that it refuses to sit still. The Spitzer thermal swings, the shifting carbon monoxide signals, the changing brightness between visits, all of it now forms a documented pattern rather than a set of isolated puzzles. Astronomers have learned to schedule repeat visits to this planet the way geologists revisit an active volcano, expecting difference rather than repetition. That expectation is itself the discovery. Nearly everything else in the night sky earns trust by consistency. The same brightness, the same period, the same spectrum, decade after decade. This small world has instead earned a different kind of standing, as the rocky planet most likely to look different the next time we check. Somewhere in that inconstancy is a mechanism, volcanic, atmospheric, or something unguessed, and whoever pins it down will have explained one of the most closely watched mysteries in the catalogue. There is one more human chapter in this planet's file, and it belongs to the amateurs. Because the host star is visible to the naked eye, 55 Cancri occupies a unique niche in public astronomy. It is the exoplanet people can point at. Astronomy clubs use it exactly that way, on winter and spring evenings, steering newcomers' eyes to a faint star in Cancer and delivering the facts like a card trick. The star you are looking at has 5 planets. The nearest one is twice the width of the Earth. Its year is 18 hours. Its ocean is molten rock. No telescope required, no photograph, just a point of light and the knowledge of what rides around it. People remember the moment, and the reason they remember it is the reason this item anchors our list. Knowledge usually keeps its distance from experience. Here, for once, the two touch. The strangest sky fact many people will ever learn is attached to something their own eyes can hold. It is worth being precise about what a magma ocean actually is, because the phrase can slide past the ear like scenery. Rock melts, depending on its type, somewhere between roughly 700 and 1200 degrees Celsius. The day side of 55 Cancri runs at double the top of that range. At those temperatures, silicate rock does not merely soften into slow lava, the syrupy kind that creeps down volcanic slopes on Earth. It thins, running fluid as water, and it begins, at the hottest points, to evaporate, lofting a mist of rock vapor the way warm seas loft humidity. The Dayside Sea is therefore not a lake of sluggish lava, but a genuine ocean, with currents, evaporation, and in some models, weather made of stone, mineral clouds condensing high over the sea and raining rock back into it. Earth itself passed through this state once, in its first tens of millions of years, when the collision that made the moon left the whole world molten. Our planet's magma ocean froze over 4.5 billion years ago and became the floor of everything that followed. On 55 Cancri, that primordial chapter never ended. The planet is a window into the Earth's own first morning, held open 41 light-years away. The night side completes the strangeness, because the same measurements that mapped the dayside heat found the far hemisphere over 1,000 degrees cooler. That gradient makes the terminator of this world, the ring where day hands over to night, one of the most extreme boundaries in the known universe, a line where an ocean of glowing rock gives way, over some unmapped distance, to a hemisphere dark and cool enough for stone to harden. Some models paint the night side as a solid crust, a black lid of frozen rock under permanent stars, possibly swept by winds of condensing rock vapor arriving from the bright side and snowing minerals onto the dark. A world half sea of fire, half field of stone snow, joined at a seam no eye has seen. Every improvement in our instruments sharpens this picture a little further, and it has not yet stopped becoming stranger. There is also a simple observational reason this planet's file is so thick, and it makes a nice piece of luck to close on. Because the year here lasts 18 hours, the planet transits, occults, and completes full phase cycles faster than almost any known rocky world. An observing program that would need years to watch a handful of orbits of an ordinary planet can bank dozens of complete orbits of 55 Cancri E in a single season. The universe, in effect, set its strangest nearby rocky world spinning on fast forward, and parked it around a naked-eye star, as if to make sure we would have no excuse for failing to study it. Astronomers have taken the hint for 20 years, and the planet has answered by becoming both the best measured and least resolved rocky world in the sky, a combination that is itself the point. More data has made it stranger. That almost never happens, and when it does, it usually means something true and new is waiting underneath. Every planet so far, however extreme, at least orbits where planets are supposed to orbit, close to their stars, in the neighborhoods where worlds are born. The next planet on our list does not. It stands 700 times farther from its suns than the Earth stands from ours, alone in the dark past the edge of its own solar system, and nobody can explain how it got there. Number 3. The planet that should not be where it is. Almost everything on this list so far has been discovered the indirect way, through wobbles in starlight or shadows crossing a stellar face. Astronomers infer the planet, calculate the planet, model the planet, but never see the planet. The third world on our list is different. We have photographed it. It appears in actual images as an actual point of light, a young giant glowing with its own heat. And that is fitting, because the strangest thing about this planet is not its weather or its substance or its chemistry. The strangest thing about this planet is where the photograph shows it standing. The system is called HD 106906, and it lies about 336 light-years away, toward the southern constellation Crux, in a sprawling nursery of young stars. At its center is not one star but two, a tight pair of bright young suns, locked in a mutual orbit, so close they complete it in about 10 days, wrapped in each other's gravity, shining together. The pair is barely 13 million years old. Against the Earth's age of 4.5 billion years, 13 million is infancy. If the Earth's history were compressed into a single year, a 13-million-year-old system would be about 1 day old. This is a solar system still in its delivery room, its planets newly assembled, its debris not yet swept. In 2013, a team led by Vanessa Bailey, then a graduate student at the University of Arizona, was studying this young pair with the Magellan Clay telescope in the mountains of Chile, using an adaptive optics system that unblurs the sky by flexing a mirror hundreds of times per second. In the images, far from the twin stars, sat a faint, warm point of light. Follow-up confirmed it was no background star. It was a planet, glowing in the infrared with the leftover heat of its own formation, about 11 times the mass of Jupiter, so young its temperature still runs near 1,500 degrees Celsius. A newborn super-Jupiter, caught on camera. That alone would have made a fine discovery. The coordinates made it a mystery. The planet, HD 106906b, stands roughly 738 astronomical units from its stars. An astronomical unit is the distance from the Earth to the Sun. Neptune, the outermost planet of our solar system, orbits at 30 of them. This planet stands at 738, 25 times farther out than Neptune, so remote that the light of its own two suns takes more than 4 days to reach it. Sunlight reaches Neptune in about 4 hours. Stand on this world, and the suns that own it are not disks. They are a bright double star among the other stars, a porchlight seen from the far end of a very long country road. A single orbit at that distance takes roughly 15,000 years. Since the end of Earth's last ice age, this planet has completed at most one lap. The problem is not that the distance is large. The universe is full of large distances. The problem is that a planet has no business existing there at all. Planets are built inside disks, the flat wheels of gas and dust that surround newborn stars, and we can see those disks directly, including the one around this very system. Disks thin out with distance. At 700 astronomical units, there is not enough material moving slowly enough to assemble a pebble, let alone a world of 11 Jupiter masses. Every route our formation theories offer runs out of road hundreds of astronomical units short of where this planet is standing. It is as if surveyors mapping a city found a finished skyscraper alone in the desert, past the last paved road, with no crane, no foundation lines, no construction record of any kind. So astronomers are left with origin stories, and every one of them is strange. The first is exile. The planet formed close to its twin suns, where planets are supposed to form, and then swung too near them or near another massive body, and gravity did what gravity does in close encounters between unequal partners. The smaller body was flung, hurled outward on an escape trajectory that should have ended in interstellar space, condemned to wander the galaxy alone. Except that it is still here, which requires a second miracle, a rescue. And remarkably, when astronomers searched the catalogues of stellar motions, they found candidates for the rescuers, a pair of passing stars, identified in the Gaia survey's data, that appear to have drifted close by this system near the right epoch. Their gravity, tugging at the fleeing planet at the right moment, could have lifted the low point of its orbit and left it stranded on a wide, stable loop instead of an exit ramp. In that telling, the planet is a castaway, thrown from its home and caught at the last moment by strangers, sentenced to circle the lights of a house it can never re-enter. The second story is that the planet is not really a planet at all in its manner of birth, but a failed star. Binary star systems form when a collapsing gas cloud fragments into 2 knots instead of 1. Perhaps this cloud tried to fragment into 3, and the third knot came up short, gathering only 11 Jupiter masses, far below the threshold to ignite. In that telling, HD 106906b is the family's stillborn third sun, orbiting at the enormous distances typical of stellar companions. The mass ratio makes this awkward, but not impossible. The third story is adoption. The galaxy, we now believe, is full of rogue planets, worlds without stars, wandering the dark between systems. A young system's gravity can, on rare occasions, capture one as it drifts past. Exile, failed star, or adopted drifter. Take a moment to notice that those are the reasonable explanations, the short list left after the impossible ones were crossed out. There is physical evidence that something violent happened here, and it is written across the whole system. The twin stars wear a debris disk, a ring of dust and comet stuff like our own Kuiper belt, and it is visibly wrecked. One side of the disk is stretched into a long, thin spike, a needle of scattered material pointing out of the system, while the other side is blunt and truncated. Something massive has ploughed through or repeatedly harassed this disk. In 2020, astronomers assembled 14 years of Hubble Space Telescope images and measured the planet's actual motion, a crawl of a few milliarc seconds, the apparent width of a coin seen from thousands of kilometers, and from it they constrained the orbit. The answer deepened the picture. The planet's path appears elongated and tilted about 21 degrees out of the plane of the disk, exactly the kind of inclined, eccentric orbit an ejected and rescued world would keep as a scar, and exactly the kind of orbit that could account for the disk's mangled edge if the planet dives near it on each 15,000-year pass. And here is where this distant stranger's file turns around and points directly at home. Our own solar system has, at its far edge, a standing mystery. The most distant icy bodies beyond Neptune do not orbit randomly. A number of them bunch their orbits in a way that looks shepherded, as if some unseen mass were quietly organizing them. That is the case for Planet 9, a hypothesized world of perhaps 5 to 10 Earth masses, orbiting our own Sun at hundreds of astronomical units, dark, cold, and so far unfound, despite years of searching. The proposal has always carried one soft objection, which is that it sounds outlandish. A giant planet orbiting that far out on a tilted eccentric path around an ordinary star. Nothing like that had ever been seen. HD 106906b is the answer to that objection. It is the existence proof. It demonstrates, in an actual photograph, that a giant world can ride a distant, inclined, eccentric orbit around a normal system and remain there stably for millions of years. When the Vera Rubin Observatory's decade-long survey of the southern sky settles the Planet 9 question, and it is expected to settle it one way or the other, this exiled world 336 light-years away is the template the answer will be measured against. The strangest address in the exoplanet catalogue might also be a mirror, showing us the outer edge of our own home. The open questions here are total. Exile, failed star, or capture, no verdict has been reached, and each story leaves fingerprints the next decade of observations could find. What is not in question is the photograph. There is a world 11 times the mass of Jupiter standing 738 times farther from its suns than you stand from yours, in a place where nothing that large can be built, and it has been there, patiently completing its 15,000-year lapse since before our species existed. Direct imaging, the technique that caught this world, is worth appreciating for a moment, because it is the hardest trick in the Planet Hunter's book, and the reason nearly everything else on this list was found by shadow or wobble instead. The difficulty is contrast. A star outshines its planets by factors of millions to billions. Photographing a planet beside its star has been compared, fairly, to photographing a firefly hovering beside a lighthouse from kilometers away through heat shimmer. Two inventions make it possible at all. The first is the coronagraph, a mask inside the telescope that blots out the star's direct blaze, an artificial eclipse manufactured on demand. The second is adaptive optics, a thin deformable mirror that reshapes itself hundreds of times each second to cancel the blurring of Earth's atmosphere in real time, unbending the starlight as fast as the sky bends it. Even with both, the method mostly works only for planets that are young, massive, and far from their star's glare, worlds still glowing with formation heat, radiating their own infrared announcement. Which is why the direct imaging catalogue is a gallery of newborn giants at scandalous distances, and why HD 106906b, young 11 Jupiters, and enormously far out, was one of the rare worlds the technique could catch. We photograph the exceptions. The exiles are the planets that can be seen at all. The scene from the planet itself is worth composing carefully, because it is one of the loneliest vantage points physics currently offers. At 738 astronomical units, the two suns of home have merged, to the naked eye, into a single brilliant point. Run the arithmetic on their combined light, and the answer lands in strange territory. That point would deliver only a few times the light of our full moon. Noon on this planet is a bright moonlit night on Earth. A landscape there, if the young giant had a surface to stand on, would lie in permanent silver twilight, sharp shadowed under one overwhelming star that is not quite a sun anymore, surrounded by thousands of ordinary stars that no longer look much dimmer than it. Home, from that distance, is not warmth or daylight. It is merely the brightest thing in the dark, a porch light at the end of a road 15,000 years long. And unlike a marooned ship, The planet is not drifting home. Its orbit is its sentence. It will still be tracing this same slow loop when our own species' descendants, whatever they have become, have forgotten the constellation it lives in. There is a wider lesson in this system that astronomers have taken to heart, and it changes how the whole galaxy reads. The processes on display here, ejection by gravitational violence, rescue by passing stars, are not rare accidents. They are ordinary weather in the crowded nurseries where most stars are born. Stars form in clusters, packed close, their infant planetary systems brushing against one another's gravity for millions of years before the cluster disperses. Simulations of those environments show planets being stripped, swapped, and flung constantly. The galaxy's population of rogue planets, worlds sailing starless through interstellar space, is now estimated in the billions at minimum, and some surveys argue rogues outnumber the stars themselves. Every one of those wanderers is a version of this planet's story with an unhappier ending, an exile that no passing gravity caught. HD 106906b is the rare case we can still see, the throne world that stayed on the property, and it stands as visible proof of a process that has quietly populated the dark between the stars with more worlds than all the suns combined. There is even a modest role in this story for the future of our own maps. The same survey machinery now coming online to settle the Planet 9 question, above all the Vera Rubin Observatory with its decade-long movie of the entire southern sky, will also sweep up distant exiles like this one around other stars, and free-floating worlds between them in unprecedented numbers. Within the decade, the file that holds this planet as an isolated oddity is expected to become a census. Either the galaxy is full of stranded giants, which would tell us planetary systems everywhere pass through early ages of violence, or exiles are vanishingly rare, which would make this one stranger still. Both answers are worth having, and one of them is coming. There is one more inevitability in this system worth recording, and it is the quiet one. The planet's glow is alone. 11 Jupiter masses of newly assembled matter hold an enormous store of formation heat, and that store is all the light this world has, because no meaningful warmth reaches it from suns 4 light days away. It shines now at 1,500 degrees, brightly enough for our cameras, precisely because it is a newborn. But there is no furnace inside to refill it. Over the coming hundreds of millions of years, the exile will radiate its birth heat away and dim, first out of reach of our instruments, then out of reach of any plausible instrument, cooling toward the temperature of the space around it. The photograph humanity took in 2013 caught a brief phase, the one interval in this world's endless future when it happened to be visible at all. Every 15,000-year lap after that will be run in growing darkness, an enormous planet circling a distant porch light, progressively less findable, never gone. An exiled planet, at least, survives its strangeness. Its orbit is stable, its distance is a kind of safety, and it will keep its lonely circuit for eons to come. The next planet on our list has no such luck. It orbits so close to its star that it is being pulled apart as we speak, and astronomers have measured the date of its death. Number 2. The planet being eaten by its star. Every planet we have visited tonight, however strange, shares one unspoken property. They persist. The backward giant will keep orbiting backward. The burning ice will keep burning. The darkest world will go on swallowing its daylight for billions of years. Whatever else the universe has done to these planets, it has let them continue. The second planet on our list has been denied that. It is dying, in plain view, on a schedule, and it is the first world in history whose ending astronomers have measured while it happens. About 1,200 light-years away, in the constellation Auriga, the charioteer, there is a yellow star, quite similar to our Sun, catalogued as WASP-12. It was surveyed by the same modest array of camera lenses that found the backward planet at number 9, the Super WASP project, patient photographer of 1,000,000 stars. In 2008, those cameras caught a giant planet crossing this star. The numbers, even by hot Jupiter standards, were alarming. The planet, WASP-12b, carries about 1.4 times the mass of Jupiter, and it completes a full orbit in 26 hours. Its year is shorter than Earth's day. It rides just over 3 million kilometers above its star's surface, about 9 times the distance from the Earth to the Moon. Mercury, the closest planet our solar system permits, keeps almost 20 times that distance from the Sun. WASP-12b orbits inside the margin our own system left as a safety zone, skimming the fire. That proximity does 3 things to a planet, and WASP-12b exhibits all 3 like a demonstration model. The first is heat. Its day side runs around 2,300 degrees Celsius, among the hottest planetary surfaces known, hot enough that exotic molecular chemistry takes over, and remarkably, the planet turns black. Hubble measurements in 2017 found WASP-12b reflects at most 6% of the light that strikes it, and likely far less, darker than fresh asphalt. At these temperatures, even the clouds that darken other hot Jupiters cannot form, and hydrogen itself begins absorbing light directly. So picture the object correctly from the start. Not a bright Jupiter gleaming beside its star, but a pitch-dark giant, glowing sullen red at its edges, circling a yellow sun once per day. The second thing proximity does is deform. Gravity weakens with distance, which means the star pulls measurably harder on the planet's near side than on its far side. On Earth, that same differential from our small moon politely lifts the oceans a few meters, and we call it the tide. At 3 million kilometers from a star, the differential is monstrous. WASP-12b is stretched along the line toward its star into a distorted, elongated shape. Astronomers detected this directly in the way the planet's light varies, and it became the first planet confirmed to be visibly deformed, a world pulled out of roundness. The technical description is that it fills most of its Roche lobe, and the term deserves 1 sentence of respect, because it is about to matter. The Roche lobe is the invisible teardrop-shaped boundary around a planet inside which the planet's own gravity is still in charge. Material inside the lobe belongs to the planet. Material carried beyond it belongs to the star. WASP-12b's swollen, superheated atmosphere reaches essentially to that boundary, and at the teardrop's point, the boundary touches open space in the direction of the star. Which brings us to the third thing proximity does. It steals. In 2010, ultraviolet observations with the Hubble Space Telescope confirmed what the geometry demanded. WASP-12b is overflowing. Its atmosphere, bloated past its own gravitational property line, is pouring through the point of the teardrop and streaming toward the star in a river of gas. The measured loss runs on the order of 10 million tons every second. 10 million tons is roughly the mass of 30 fully loaded supertankers, leaving every second, forever. The planet is not being dramatically ripped apart in some single act of violence. It is being drained, continuously, the way a wound bleeds, matter siphoned off the day side and swallowed into the star that lights it. The theft has left evidence all around the crime scene, and the evidence is strange enough to deserve its own mention. So much gas has been pulled off WASP-12b that the shed material now shrouds the entire inner system in a thin, translucent veil. Astronomers noticed something odd about the star itself. Its spectrum is missing the ultraviolet glow that active sun-like stars always emit from their upper atmospheres, as if the star were unusually, almost impossibly quiet. The accepted explanation is that the star, is not quiet at all. It is veiled. The planet's own stolen atmosphere, dispersed into a cloud around the star, absorbs that glow before it can reach us. The planet has, in dying, wrapped its executioner in a shroud. We observe the star through a fog of consumed planet. And then there is the discovery that promotes WASP-12b from extreme to genuinely historic. Transits make wonderful clocks. Every time the planet crosses its star, it stamps a timestamp, and WASP-12b stamps one every 26 hours, and astronomers have been collecting those stamps since 2008. Year after year, the stamps began arriving early. Not dramatically early. A few seconds, accumulating. For a while, there were two candidate explanations: a slow pivot of an eccentric orbit that merely mimics decay, or the real thing. The question was settled by careful timing work reported in 2020 and confirmed with the TESS Space Telescope's independent measurements in the years right after. The mimic was ruled out decisively. The orbit of WASP-12b is shrinking. Its year shortens by about 29 milliseconds with each passing Earth year. 29 thousandths of 1 second. It is among the most delicate changes ever measured about another world, and it is a death sentence, because the arithmetic only runs one direction. The orbit tightens, the tides strengthen, the drain quickens, the orbit tightens further. Follow the 29 milliseconds forward and the spiral ends, with the planet torn apart at the Roche limit and swallowed, in roughly 3 million years. 3 million years sounds like an eternity, so let it be measured against the right rulers. Against a human life, it is fathomless. Against the universe, it is nothing at all. The star WASP-12 will live for something like 10 billion years. Its planet's remaining time amounts to 3/10,000ths of that span. If the star's whole life were a single year, the planet would have about 2.5 hours left. And here is the ruler closest to home. 3 million years ago, on the plains of East Africa, our ancestors were shaping the oldest stone tools ever found. The interval separating you from the first sharpened rock is the same interval separating WASP-12b from its ending. Everything that has ever happened to our kind, from the first tool to this sentence arriving in your ears, fits inside the time that planet has left. Ride, for a moment, alongside the stream. You are above the day side of WASP-12b, holding position where the planet's teardrop narrows toward its point. Below you, a horizon stretched wrong, a giant's edge pulled long like soft glass, black on black, rimmed in dull red heat. Ahead of you, filling half of everything, the star, a wall of yellow-white fire with no top and no bottom. And between them, passing you in silence, the river. A broad luminous current of the planet's own substance, hydrogen sifted with sodium and magnesium, flowing off the world below and out through the point where its gravity ends, unspooling toward the fire ahead. It does not look violent. That is the unsettling part. It looks patient, a ribbon of light easing from the dark shape into the bright one, 10 million tons in the second you watch, and the same again in the next second, and the planet does not resist, because nothing this large resists anything. It only continues, and continues less. The scientific afterword is that WASP-12b's dying is itself a discovery about stars. The rate of that 29 millisecond decay reveals how efficiently the star's interior absorbs and dissipates the energy of tides, and the measured value came out far higher than standard stellar models predicted, which means something about the inside of that sun-like star behaves in a way our theory of stellar interiors did not anticipate. The death of this planet is, quite literally, functioning as a probe of the anatomy of its star. Astronomers also now watch other ultra-close giants with new suspicion, checking their timestamps for the same slow drift. WASP-12b is merely the first world we have watched begin to end. The catalogue of the dying has almost certainly only begun. Here is the register in which to hold this one. Astronomy mostly shows us permanence, orbits that outlast civilizations, light older than our species. WASP 12b is the correction. The sky is not a finished painting. It is a process, with losses scheduled, and for the first time in the history of our kind, we have read one entry in the schedule. A world will end, we know which one, and we know approximately when. The timing measurement that revealed the spiral deserves to be walked through slowly, because it is one of the most delicate feats of bookkeeping in the history of astronomy, and its logic is beautiful. A shrinking orbit does not announce itself as drama. It announces itself as punctuality gone slightly wrong. If the orbit shortens by 29 milliseconds per year, then each year's transits arrive a hair sooner than a fixed schedule predicts, and the error compounds. After 1 year, the planet is early by a blink no clock on a bedside table could show. But transit timing is cumulative, and the discrepancy grows with the square of the elapsed time, the signature arc of steady acceleration. After a decade of observations, WASP 12b's transits were arriving minutes ahead of the old schedule, and minutes are an enormity in a field that measures shadows to the second. Plotted across 12 years of data, from the Discovery cameras through amateur observations to the TESS Space Telescope, the timing residuals traced a clean, unmistakable downward parabola, the geometric fingerprint of decay, incompatible with the rival explanation of a slowly pivoting eccentric orbit. It is worth noticing who contributed those points. Alongside the professional observatories, years of the timing record came from skilled amateurs, measuring transits from backyard and club telescopes, feeding their timestamps into shared databases. The discovery that a planet is falling into its star rests, in part, on the patience of people who did it for love on their own rooftops. The physics behind the fall is its own quiet marvel, because gravity alone would never do this. Orbits do not decay by being close. They decay by losing energy, and the thief here is the tide. The planet's gravity raises a bulge on its star, a standing swell in the stellar surface that tries to track the planet around. But the star's interior is not frictionless. The bulge lags, dissipating orbital energy into the star's depths as heat, and the orbit pays the bill, contracting year by year. The rate of that contraction, therefore, reads out a hidden property of the star, how efficiently its insides turn tidal motion into warmth, a quantity stellar physicists label with the letter Q and argue about endlessly, because it cannot be measured any other way. WASP 12b's 29 milliseconds implied a star hundreds of times more dissipative than standard models of sun-like stars predicted. Theorists now suspect this star has quietly evolved off the main sequence into a structure whose interior swallows tides greedily, or that some resonance in its depths is amplifying the friction. Either way, the dying planet is functioning as a probe, sounding the interior of its own executioner with its final orbits, telling us things about stellar anatomy that no other instrument can reach. As for the ending itself, astronomy no longer needs to imagine it, because in a first for our species, we have now watched it happen elsewhere. In May of 2023, astronomers reported that a sun-like star, 10,000 light-years away, in our own galaxy, had been caught engulfing a planet. The event announced itself as a brief, strange brightening, a star flaring up over days and then subsiding, sheathed in cool dust, exactly the signature models predict when a world spirals through its star's surface and dissolves. The swallowed planet was likely a hot Jupiter, much like WASP 12b, at the end of exactly the road WASP 12b is now walking. So the final chapter can be written with confidence. 3 million years from now, the black egg of Auriga crosses its Roche limit fully, comes apart over a handful of orbits into a brilliant shredded stream, and the star dines and brightens briefly, a flare lasting days, marking the digestion of a world that had circled it for billions of years. Any astronomers alive in the galaxy at that hour will see a modest transient in Auriga, catalogue it, and move on. Unless their records are very good, they will never know the event had been on humanity's calendar for 3 million years. Before we leave this world to its arithmetic, it is worth sorting out the strange double honor it holds in the catalogue, because darkness has come up before tonight. Measurements place WASP-12b's reflectivity at most around 6% and plausibly near zero, which makes it a genuine rival to the Ember of Draco at number 7. The two planets earn their darkness differently. TREES-2b absorbs light with a chemistry of sodium, potassium, and titanium oxide in a merely very hot atmosphere. WASP-12b is hotter still, so hot that molecules themselves struggle to survive on its day side, and the absorption is done in part by hydrogen broken open by the heat. One is dark like a coal cellar, the other dark like the inside of a furnace with the door shut. That the same list of 10 planets contains both, along with a mirror-wrapped steam world reflecting half its light, says something worth keeping. The galaxy is not sampling gently around familiar averages. It is filling out the extremes of every axis at once, as if the full parameter space were a checklist, and somewhere on the list of boxes, ticked early, was a black egg emptying itself into a yellow star. Stand once, briefly, in the sky of this world, on the night side, the only side where standing is even a thought experiment. Above you, stars, ordinary and calm. But around the entire rim of the world, the horizon burns. In every direction, the edge of the sky glows with the light of the star that fills the space beyond the planet's own shadow, a circular dawn that never breaks, 360 degrees of imminent sunrise that has been imminent for billions of years. The ground beneath you, if the word applies, streams. You can feel, in principle, the direction of the theft, the far side of the world being planed away, the substance of the planet migrating overhead in a thin, high wind bound for the point of the teardrop. It is the only place on this list where the strangeness has a direction and a destination. Everything here is moving, patiently, toward the light at the rim. The lineage of this planet is worth one closing thought, because it makes the arc of the whole field visible. The first exoplanet ever found around a sun-like star, in 1995, was a hot Jupiter, a giant improbably close to its star, and the discovery was so contrary to expectation that some astronomers initially doubted it could be a planet at all. 30 years later, the hot Jupiters have gone from impossible to foundational, the best-studied class of worlds in the sky, and WASP-12b stands at the far end of their spectrum, the specimen pushed to every limit at once, hottest, blackest, most distorted, and terminally close. It is what the founding discovery of the field looks like, taken to its conclusion. The class of planet that opened the exoplanet era is also giving us our first measured planetary ending, and there is a strange tidiness in that, the story's first character type volunteering to demonstrate how the story ends. A dying planet is, at the very least, a planet we can see, measure, and mourn on a timetable. Number 1 on this list offers no such comfort. It was seen for 56 days, through its shadow alone, by cameras that did not know what they were recording. It has never been seen again. And if the interpretation of that shadow is correct, it is wearing the largest structure ever attributed to any planet, anywhere. Number 1. The planet we only ever saw once. Every list like this one makes a quiet promise that its final entry will justify the descent. Here is ours. The strangest planet in the known universe is a world astronomers have never actually seen. It announced itself exactly once, over 56 days in the spring of 2007, by casting the most complicated shadow ever recorded, and then it withdrew into the dark and has not been found since. If the leading interpretation of that shadow is correct, this object carries a ring system 200 times the size of Saturn's, wide enough to reach from our Sun most of the way to Venus, and somewhere inside those rings, there may be a moon the size of a planet, sweeping a lane clear in the way moons do. Nearly 2 decades of searching have produced no second look. What remains is one long, strange record of a star's flickering light, an interpretation almost too spectacular to believe, and a community of astronomers, professional and amateur, who check that star night after night, waiting for the shadow to come back. The story begins with an instrument this list has already praised twice, and there is a pleasant symmetry in that. The Super WASP survey, the array of humble camera lenses that found the backward planet at number 9 and the dying planet at number 2, spent years photographing the southern sky every clear night, recording the brightness of hundreds of thousands of stars. Among them was a young orange star about 450 light-years away in Centaurus, catalogued by its coordinates as 1 SWASP J140747, and known today, more mercifully, as V1400 Centauri. The star is about 16 million years old, a member of the same generation of newborn stars as the exiled planets family at number 3. In April and May of 2007, the cameras dutifully recorded something happening to this star. Nobody noticed. The measurements went into the archive, joined hundreds of millions of others, and sat there. The finding came years later, and it belongs to a tradition this channel holds in particular affection. Discoveries made not at the telescope but at the desk, in data everyone already had. Around 2010, the astronomer Eric Mamajek and his group at the University of Rochester, including a graduate student named Mark Picourt, were studying young stars in exactly this region, using the Super WASP archive to check their targets for ordinary variability. When they pulled the file on this one orange star, they found something with no precedent in any catalogue. For 56 days, the star's light had convulsed. This was not the neat, shallow, symmetrical dip of a planet transiting, the kind of signal we have met all night. The star plunged and partially recovered and plunged again, dozens of times, in a jagged, layered sequence. At its deepest, 95% of the starlight was gone. Something had passed between that star and every telescope on Earth, and the something had structure, fine, banded, organized structure, tens of millions of kilometers of it, marching across the line of sight for 8 weeks. The team published in 2012, and the interpretation that has framed the object ever since arrived with a memorable nickname, Saturn on steroids. The idea runs as follows. A massive companion, unseen, orbits this young star on a long, eccentric path. Around that companion tilts an enormous disk of rings, and in 2007, companion and rings happen to cross directly in front of the star as viewed from Earth. Each ring edge, passing the star, stepped the light down or up. The jagged 56-day record is, on this reading, a scan of the ring system, edge by edge, gap by gap, the way a barcode reader sweeps a label. In 2015, Matthew Kenworthy of Leiden Observatory, working with Mamajek, fit the record in detail. The model that emerged still stands among the most astonishing objects ever proposed in planetary science. At least 37 distinct rings. An outer radius near 90 million kilometers, roughly 6/10 of the distance from the Earth to the Sun. A total span 200 times that of Saturn's rings, holding roughly an Earth's mass in dust and debris. Saturn's rings, the most beautiful structure our solar system ever built, the crown we placed on the whole idea of what a planet can wear, would sit inside this system like a wedding band lying on the floor of a stadium. Numbers that size deserve the yardstick we packed at the very beginning of the list. From the surface of the first planet tonight, you may remember, a red star hangs fixed in the sky, 4 times the width of our full moon, and that felt enormous. So now perform the standard thought experiment, the one the discoverers themselves offered. Lift the rings of J1407b and install them around Saturn. From your backyard, they would span many full moons laid end to end, a banded oval wider than any object in our night sky, bright enough to be plainly visible at dusk, casting shadows at midnight, visible in broad daylight. Human history would simply have been different. Every mythology on Earth would have grown up beneath a ringed banner, and the first question every child asked about the sky would have been about the rings. The full moon, our default unit of celestial grandeur, would have been the second most interesting thing overhead. And the record holds one more detail, the one that elevates this from spectacle to genuine wonder. In the middle of the 56-day sequence, the light curve shows at least one clean, wide gap, a stretch where the rings apparently thin to almost nothing at around 61 million kilometers from the companion's center. Planetary scientists know exactly what such gaps mean, because Saturn teaches the lesson locally. Gaps are swept by moons. An embedded moon, orbiting inside a ring system, gravitationally clears its own lane, the way a snowplow keeps a road open through a storm. The width of this gap suggests a body somewhere between the mass of the Earth and the mass of Mars. Follow that chain of inference to its end, and hold what sits there. Orbiting an object we have never seen, inside rings we measured only by their shadow, there may be a world the size of ours, a moon in the process of being born, clearing its lane in a structure 200 times the size of Saturn's rings. If confirmed, it would be the first moon beyond our solar system ever detected, found not by its light, but by the tidiness of its housekeeping. Now comes the honest turn, because this list promised honest labels, and number 1 requires the most honest label of all. Everything above rests on a single event. The companion itself, the ringed body called J1407b, has never been directly detected. Not in 2007, not since. And the follow-up campaign has been long, serious, and increasingly puzzled. The eclipse model requires the companion to return periodically, on an orbit somewhere between several years and a couple of decades, yet dedicated monitoring, including a global network of amateur astronomers coordinated through variable star organizations, has watched V1400 Centauri for the better part of 2 decades and caught no second eclipse. Attempts to see the companion have fared no better. Its mass is only loosely bracketed, most likely between 13 and 26 Jupiter masses, which would make it not a planet in the strict sense, but a brown dwarf, a failed star, a distinction that matters to taxonomists and does nothing to shrink the rings. A 2017 dynamical study added a genuinely strange requirement, that for the ring system to survive its close passages to the star without being shredded, the rings very likely orbit their host backward, retrograde, spinning against the direction of the companion's own path, a configuration with no analog anywhere in our solar system. We have met a backward orbit tonight, at number 9. This would be a backward crown. Then the radio telescopes complicated everything. In 2017, observations with the ALMA array in Chile, sensitive to the cold millimeter-wave glow of dust, found a faint source near the star, but measurably offset from it, not where a bound companion was expected to be. That opened a possibility that sounds like fiction and is published science. The ringed object might not belong to this star at all. It might be a free-floating body, a rogue ringed world drifting through Centaurus that happened, in 2007, to pass exactly across the one line of sight along which humanity keeps cameras. If so, the eclipse will never repeat, the rings are gone from our sky forever, and the whole event was a one-time crossing, witnessed by accident, unrepeatable by definition. And in 2024, A deeper ALMA observation looked again for that offset source and failed to recover it, deepening the confusion rather than resolving it. Every layer of scrutiny has made the object less settled, not more. So here is where the strangest planet in the known universe actually lives tonight. Not on any star chart. It lives in 56 days of photometry from 2007, data that is real, public, and reanalyzed many times, always with the same conclusion, that something enormous and finely structured crossed that star. It lives in a set of competing explanations, a ringed giant on a long orbit, a rogue ringed wanderer, or something not yet imagined, none of which can currently be confirmed. And it lives in the nightly attention of people who refuse to stop checking. That last part deserves a moment, because it is the most human thing in this entire countdown. Somewhere tonight, amateur astronomers, school teachers and retirees and engineers with backyard telescopes will point their instruments at one unremarkable orange point in Centaurus, measure its brightness, and log the number, as their community has done for years, on the chance that tonight is the night the light begins to stutter again. If the eclipse returns, it will not arrive as a headline first. It will arrive as a data point on a volunteer's screen, a star a fraction dimmer than it should be, and then another point, and another, and someone at a kitchen table will be the first human being in decades to watch the shadow of the rings come back. Imagine, one last time tonight, standing where no one has stood. You are on the surface of the moon that may exist, the Earth-sized lanekeeper, far inside the ring system of J1407b. There is no ground in view in any direction that is not sky, because the sky here is the structure. The ring plane rises from one horizon, arches overhead, and descends to the other, a highway of banded light and shadow, thousands of times wider than any rainbow, its inner edges bright with the small light of the distant orange star, its outer reaches fading into the dark like a road at night. Along the whole arch, the bands slide past one another with the patience of clock hands, black gaps and pale lanes keeping their spacing across millions of kilometers. Directly above you runs the one clear channel your own small world has swept for itself, a ribbon of honest starlight cut through the glow. Nothing here hurries. The rings turn, the star burns quietly at its distance, your borrowed moon keeps its lane. It may be the grandest view the galaxy offers anywhere, and no one may ever confirm that it exists. It waits, if it waits at all, on the far side of a shadow we saw one time. History, as it happens, holds a precedent for a mystery of this shape, and it is a comfort worth including. In the constellation Auriga, where our dying planet at number 2 resides, there is a bright star called Epsilon Aurigae that has puzzled astronomers since the 1820s. Every 27 years, it dims for nearly 2 full years, far too long for any eclipsing star to explain, and for over a century, the cause was one of astronomy's standing embarrassments, with proposed culprits ranging from strange semi-transparent stars to enormous clouds. The modern answer, assembled patiently across generations and finally imaged directly in 2009, is that the star is periodically eclipsed by a companion wrapped in an immense dark disk of dust, a flattened structure hundreds of millions of kilometers across, seen nearly edge-on. In other words, the sky has shown us giant disk shadows before, and that mystery took roughly 180 years of returning eclipses to crack. The eclipse of V1400 Centauri has happened, so far as we know, once. By the standards of Epsilon Aurigae, this investigation is not stalled. It is merely young, a few pages into a file that stars of this kind have taught us can run for centuries. The fine structure inside those 56 days deserves a closer look too, because the details are what force the spectacular interpretation. On several nights within the eclipse, the star's brightness changed drastically within a matter of hours, plunging or recovering at rates that require the occulting material to have edges, sharp, well-defined boundaries sweeping across the stellar disk at tens of kilometers per second. Smooth clouds do not do that. Sharp-edged, concentric structures do. The light curve rules out a formless blob as thoroughly as it rules out a simple planet, and that double exclusion is the whole case for rings. Whatever crossed the star was enormous, organized, banded, and internally gapped, with edges crisp enough to switch the starlight in an afternoon. Astronomers have tried repeatedly to build an alternative that fits those constraints without rings, and the alternatives keep coming out stranger than the rings themselves, which is, in its own way, the purest possible definition of this list's number one. The follow-up campaign has its own quiet heroism, worth a paragraph in any telling of this story. Kenworthy and his collaborators did not simply wait for luck. They organized. Observatories across the southern hemisphere were enlisted to keep periodic watch on the star. The American Association of Variable Star Observers, the century-old alliance of amateur astronomers who monitor changing stars, formally adopted the target and has carried it for years, with observers contributing thousands of individual brightness measurements from private telescopes on multiple continents. The team even combed history for earlier eclipses, digging through archives of photographic sky plates reaching back a century, the same kind of glass plate archaeology that has solved other slow mysteries, checking whether the star had ever dipped before. The plates show no earlier event, which either means the orbit is long or the crossing was singular. Every avenue, in short, has been walked. What this object has now is what the strangest cases always end up with, a standing watch and an open file. And there is something fitting at the end of this countdown in the fact that our number one was found in an archive years after its own light show by people looking for something else. Every discovery on this list rode in on patience, small telescopes staring at ordinary stars, spectrographs listening for a walking pace wobble, photometers counting parts per million. None of it is glamorous while it is happening. The cameras that recorded the rings did not know they were recording anything. The measurements slept in a database for years, filed under an anonymous number, while the astronomers who would eventually understand them went about other work. The strangest planet in the known universe spent half a decade as an unexamined row of numbers on a server. It makes you wonder, in the most pleasant way available at this hour, what else is already sitting in humanity's archives tonight, measured, recorded, backed up, and not yet noticed, waiting for its mamajek to open the right file. A note on taxonomy belongs here, briefly, because the object's uncertain mass straddles a boundary that astronomers care about. Below roughly 13 Jupiter masses, an object cannot ignite any nuclear reaction and is unambiguously a planet. Above that line, up to about 80 Jupiter masses, it can briefly burn a trace isotope of hydrogen and is classed a brown dwarf, a failed star. J1407b's estimates span the line itself. If it sits below, it is the most extravagantly dressed planet ever proposed. If above, it is a small failed star wearing a planet's crown. The honest answer is that the label is the least important thing about it. Whatever category claims the object, the rings are the phenomenon, and rings 200 times Saturn's span are equally impossible sounding on either side of the line. And the rings themselves may be something better than decoration. Remember the system's age, 16 million years, the same cosmic infancy as the exile at number 3. Saturn's rings are thin, old and sterile, shaved ice circling a finished planet. A structure like J1407b's, immense, massive and gapped, around an object this young, matches something else in our theories rather precisely, a circumplanetary disk, the construction site from which moons are born. Jupiter's 4 great moons, the ones Galileo found, condensed out of exactly such a disk 4.5 billion years ago. If that reading is right, the 2007 eclipse was not a portrait of a decoration. It was a photograph of creation in progress, a moon system midway through being built, with the gap marking the first finished child. We may have caught, for 56 days, the one process every moon in our own sky went through, in the act, and then lost the construction site in the dark. If the shadow does return, the plan is ready, and it is worth hearing, because it shows how much can be extracted from a second chance. A returning eclipse, caught in its opening hours by the standing watch, would trigger spectroscopy across every available wavelength, reading the ring's composition as starlight filters through each band in turn, ice or rock or dust, ring by ring, like a prism run through a comb. Precise timing of each edge would map the system's geometry to fine precision, confirm or retire the moon gap, and pin the orbit at last. A single repeat performance would convert nearly every open question in this item into a measurement. That is what the watchers are actually waiting for, not merely a light going dim, but the one observing night that would turn the strangest entry in the planetary catalogue into the best mapped ring system beyond Saturn. The distance between those two outcomes is one shadow, and shadows keep their own schedules. And with that, the countdown is complete, so let the whole list stand in view for a moment before we set it down. 10 worlds. A false second Earth with letters on the way. A giant running its year in reverse under clouds of quartz. Ice that burns. A planet darker than coal, glowing like an ember. Blue skies that rain glass sideways. A steam world wrapped in a mirror. A magma sea that breathes its own sky and will not hold still. An exile standing where nothing can be built. A black egg of a planet, 3 million years from its ending. And a crown of rings 200 times Saturn's, seen once, wearing a possible moon, belonging to an object no one can find. At the start of tonight, we called the 8 planets of our solar system a rulebook. 10 items later, the truth has turned inside out. The 8 worlds we grew up with are not the standard from which strange planets deviate. They are the quiet exception, one calm household on a street of marvels, and every rule they taught us was only the house style. That is not a loss. It is the finest kind of correction, the kind that means the universe is bigger on the inside than the textbooks guessed, and that the catalogue of 6,000 worlds is still, plainly, an early draft. Somewhere in Centaurus, a young orange star burns steadily tonight, and patient people are watching it, and perhaps one night the watching will pay out and the strangest planet we know of will step out of its own shadow at last. Until then, it keeps its rings, and its silence, and its place at the top of this list. The stars you can see from your window tonight are the bright, steady minority, and you now know a little of what moves among them. Let the strangeness settle into something calm, because it was never a threat, only the universe being more inventive than we expected, 20 light-years at a time. The rules you learned are safe here at home. The sun will keep its familiar planets in their familiar lanes, and the strange worlds will go on being strange on your behalf, far away, all night long. Sleep well, and good night.